Hey everyone, so sorry for the delay on this video. I've just been super busy with all of my research stuff, but we are going to be covering probably the most important video that I will be making today, and that is on the attention mechanism. So this is going to be a multi-part video that's going to build up to building the original Attention is All You Need paper on language translation. So we're going to see how we get there, but I do want to chunk up what we're focusing on based on the architecture. So if we quickly look at the Attention is All You Need implementation, all of y'all have probably seen this figure at some point. This one right here. You can see there's a lot of pieces going on here, but you do have everything you need to build this. So I'm assuming that you've taken the prerequisites for this, basically all those introductory PyTorch videos that we've talked about. So if you are unfamiliar with PyTorch, just go take a look at those. You'll find them on my channel, and I'll link them in the video. But today, what we're going to focus on is these orange blocks here: multi-head attention, masked multi-head attention, and, well, multi-head attention. So this is what we'll be focusing on today. We have all this extra stuff: input embeddings, output embeddings, feed forward, add norms, and stuff. We're going to look at this later. That's a future. That'll basically be the next video, or maybe the one after that. So we're going to look at those later. For today, we're just going to look at attention. And the reason we're looking at attention is this concept of attention basically shows up in most state-of-the-art architectures today. So in future videos, when we're going to implement Roberta or GPT or vision transformers, masked autoencoders, or even some of the generative models like diffusion models, you're going to see this attention mechanism show up everywhere. So we're going to focus on attention just because it's super important, and we'll build up from there. But this video is going to kind of act as a prerequisite for basically every video I will be doing in the future. If you already know attention, then there's not a lot for you to learn here. But I will be talking about some more nuance than I was probably planning on going in to. So there's actually 3 types of attention, so none of this has to make sense yet, but the things we're going to be talking about today is self-attention, causal self-attention, so there's going to be some type of an attention mask involved there, the causal attention mask. We'll also be talking about padding in attention, how we implement that. Then we're going to talk about cross-attention, and then how padding works in cross-attention. So we're going to learn a bunch of different things, and then at the end, we're going to be writing these attention implementations, but technically, if you're going to be training a big bad model, you want to use the most efficient attention implementation possible. And so to do that, we'll be looking at flash attention. We obviously cannot implement flash attention. That's kind of beyond the scope of this because that requires fused CUDA kernel implementations. That's just too complicated for an introductory video. So maybe we'll do flash attention in CUDA in a future video. But for today, we're just going to be looking at attention and seeing how we build it. So let's go ahead and get started. I want to recap this, starting with recurrent neural networks. So again, if you are unfamiliar with recurrent neural networks, I have a whole video about recurrent neural networks, LSTMs, and some of their problems. And the main problem has to do with vanishing gradients, right? So we talked about how in recurrent neural networks, you can only pass in you can pass in any length of a sequence you want to, that's fine, but it only has the capability of learning on some number of them. Like, it can only have or remember so much history. And so the recurrent neural network has that limitation due to this back propagation through time. We're just unable to hold long context information, which isn't helpful if we want to train a language model like we have some of these big GPTs and llamas and all these other models out there today. These models have huge context lengths. You can pass in thousands of words or an entire book, and it's totally fine. It can somehow understand them, and recurrent neural networks just didn't have that capability. They did try to improve it with the LSTM, adding that additional cell state into the recurrent neural network, which acts almost kind of like a residual connection from the ResNet, though it's not exactly true, but it is kind of analogous to it. So we have some mechanism here to process sequences, but this isn't the best method. And so attention actually existed before the transformer. And so there was an attention augmented RNN. And this isn't exactly what it was doing, but this should give you a ballpark idea of what was going on. So in the RNN, what we did is we produced a X we had an input of x's, and we produced a hidden state at every single x, right? And this hidden state encodes the information at x and its history, right? And if it's a bidirectional LSTM, then it be in both directions. But let's just keep it simple and think about a single direction LSTM where this hidden state t plus 2 encodes the information from xt plus 2, but also the historical information of the sequence. But due to backpropagation through time, we could only go back so many time steps before the gradient was too small. And so because of this, the idea was, well, instead of taking all of the, taking a hidden state and predicting some yt plus 2 from it, like you see here, why not first take a weighted average of our hidden states, right? So basically we're going to be taking a weighted average of all these hidden states by some weight. So we're going to do ht times at plus ht plus 1 times at plus 1 plus ht plus 2 times ht plus 2 ... all the way up to the end. So this is a sum, or a weighted average, and these weights are learnable. So just like everything else in neural networks, these are just weights, and we can learn them, right? So it's a weighted average of our hidden states. And so this new, let's just say c plus 2, we're going to have a c for each of those. So we'll have a ct plus 1, ... c big T. We're going to have a c for all of them, but just to keep this simple, I just drew the ct plus 2 for this specific one. This ct plus 2 is a weighted average of all this information. And because these weights are learnable, the model can learn to decide, are these hidden states important? Are they not important for the purposes of predicting y2? So you can imagine ct plus 2 as kind of a global context, right? A global understanding of the sequence of how are all of these tokens related to this specific time step. And so this is our attention augmented RNN, right? We just do a weighted average of our hidden states. Now, you can imagine there's some problems with this, and we'll talk about those later, mainly to do with compute, because this becomes a fairly expensive operation, a quadratic operation. We'll see that a little bit later. But for now, what I want to mention here is, why is the paper called Attention is All You Need? The problem is this, or really the realization is this. We are actually doing the same thing twice. We are first learning a recurrent neural network on our inputs of x's, right? So these hidden states it's some information about the history of our tokens, and more importantly, it's how the tokens are related to each other, right? This ht plus 2 learns how is the xt plus 2 related to the history, right? And it does it by the weighting mechanism inside the RNN or LSTM or whatever mechanism you decide to pick. So these hidden states are some type of interrelationship between our inputs. And then the cell states, or not the cell states, the context factors, the C's, are also some type of a weighted relationship between our inputs, but the hidden states in this case. Well, doesn't it seem like we're doing the same thing twice? We're modeling sequence information here using recurrence, and then we're modeling sequence information here using attention, using these weighted average. And so the Attention All You Need paper said, well, this thing is slow because recurrent neural networks, remember, it's a for loop. We have to actually loop through one step at a time, and this is just a very painful process to go through. And it's an expensive operation because we can't utilize nice GPU parallelism to pull this operation off. We have to loop through it. On the other hand, a weighted average, and you'll see why in just a bit, this turns out just being a simple matrix multiplication. This is just a basic matrix and matrix multiplications are super parallelizable. And so the way we can kind of approach this then is, well, if we're learning a slow way of doing sequence here and then a fast way of doing sequence modeling up here, why not just do the attention mechanism? Why not calculate our context factors directly on the x's and just skip the hidden states altogether? And this was basically the novelty of the Attention is All You Need paper. They tossed the recurrence and just kept the attention, which is why it's called Attention is All You Need. There are a couple limitations, though, that we won't be touching on today, but one of them is known as the kind of the implicit nature of the recurrent neural network. The recurrent neural network understands that ht plus 1 comes after ht, and ht plus 2 comes after ht plus 1 and ht. So the sequence information is kind of embedded into the algorithm of the RNN. It's there, right? That implicit information is already there. A weighted average doesn't have that information. If we just do a weighted average of x's, it doesn't actually have the understanding that, hey, xt plus 1 comes after xt and xt plus 2 comes after xt plus 1 and t. And we'll see this in more detail in the next video. We'll draw it out when we talk about positional embeddings, but that's exactly what we need to do. We need to inject positional information into our model, into our data. We again won't be doing that today. Today we are focused squarely on how we do this attention mechanism and all the different variants that you typically see in typical attention implementation. So that's what we're going to be doing. So this is the setup for the attention is all you need. You have some inputs. You pass the same input to 3 different linear layers, queries, keys, and values. The queries and keys create an attention matrix. The values, then you do a weighted average with that. You pass it to another linear layer, and you get an output. And this sounds fancy, and we're going to be breaking this down step by step. So we're going to look at this, we're going to completely take it apart, and we're going to implement every piece that we need for it, that we'll need for our full attention is all you need implementation in the future. So for now, kind of keep this figure in mind, but this is what we're doing. And this is the actual formula, right? We're doing QK transpose. We're dividing by some constant. We'll talk about why we do that in a bit. We take its softmax, and then we take its, multiplied by the values. And so the way you should interpret, so queries, keys, and values, the way you should interpret this typically is the queries are the tokens that we're interested in. The keys are the tokens we want to compare our query against. And the values are what we will be weighting. It's the thing we'll be doing our weighted average on. And it'll all make sense in just a bit. So I have some figures here, so I'm going to try to use them as much as I can. But whenever becomes difficult, I'll start to draw stuff out as well. So let's just start here. So our queries, just again, to keep in mind, data, let's ignore the batch size for now. Sequence data is typically a sequence length, right? How many words do I have in my sentence, for example, or how many tokens do I have in my sentence? And then the embedding dimension, right? How many numbers do I want to use to represent this word? So you should have seen this when we did like the LSTM classification problem, right? We had to take our tokens, the indexes that represent every word or every character, or whatever we did, and we had to convert them to embedding. So we have the nn.Embedding matrix that does that operation for us, which is great. So this is our sequence by embedding. And queries is just a projection of this. So it's basically our sequence by embedding going through some linear layer to create our query matrix. So as you notice, our input x goes in, goes through a linear layer, produces the query. And the query and the inputs are the same shape. And we'll kind of see this in practically how it works out in just a bit. But for now, let's just think about high level. We have our query vector, and then we have our key vector, key matrix. And key is exactly the same. It's just a different projection, right? Just a new projection, but it's still the same thing, same idea. But we're going to take its transpose. And when we do query key transpose, well, we're multiplying an S by E matrix by an E by S matrix, leaving us with a final S by S matrix. And this matrix is known as the attention matrix. Okay, so in this matrix here, let's kind of see what we're doing. So this element right here, 0.2 in the top left, would be the dot product between this first vector for sequence. So let's call this first one is the first word, so word 1. And then this is the key vector for also word 1. So if you know anything, dot product similarity is also, you also have a cosine representation of them, but they represent the similarity between vectors, right? So when we have a high dot product, when these when the dot product of two vectors is large, that means they're pointing in similar directions. And when the dot product of two vectors is negative, then they're pointing in opposite directions, and so on and so forth. So there's some interpretation there, but we're just doing dot product. So this 0.2 is the dot product between the query of the first token and the keys of the first token. The 0.1 is the dot product between the queries of the first token and the keys of the second token. So this 0.1 represents how is the first word related to the second word. And then the 0.4 is how is the first word related to the third word. The 0.3 is how is the first word related to the fourth word. And we're using dot product similarity to quantify related, like how they're related to each other. And we're hoping the model can learn how are the different words, the different tokens, related to one another, right? And this kind of answers this question, right? We're trying to understand what these weights are. How is our ht plus, or in our case, it'll be x. How is xt plus 2 related to xt? How is xt plus 2 related to xt plus 1? How is xt plus 2 related to itself? How is xt plus 2 related to dot, 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 all the way up to xt? Right, so we're just trying to understand the relations between them, and for us to kind of quantify the relationship between xt plus 2 and xt, I'm just taking the dot product between those two vectors. And matrix multiplication is just a bunch of dot products, right? So we have a sequence by sequence matrix representing how every single token in our sequence is related to itself. So how are, kind of practically, if you have a sentence, how are each word in the sentence related to every other word in the sentence? And that's the key idea for the attention matrix. Now, do notice that each of these rows add up to 1. I went ahead and took the liberty of just applying a softmax to convert these to probability. So, because dot products can be anything, right? These numbers can output, any positive, negative, 0. It doesn't matter. It can be any number. Typically, that's not the way we like to think about it. We like to say that, oh, the first word is 20% related to itself, 10% related to the second word, 40% related to the third word, and 30% related to the fourth word. So it's kind of like our quote-unquote weights for our weighted average. So this sets up our QK transpose, right, producing this S by S matrix, which is known as the attention matrix, right? So there we go. So let's go ahead and, so that's stage 1. It's producing this S by S attention matrix. Now, look at the formula. We divide it by a constant and do a softmax. So assume this is the final output. So this, after dividing and doing a softmax, we produce this output here. Now we have to multiply it by the values. And again, remember, the values is just another projection of our inputs. So queries, keys, and values are just three separate projections of the exact same input. So this is a matrix of how is every word related to every other word. So here we go. We have our attention matrix. How is every word related to every other word? And the values go with every word. So our values matrix will be just like the queries matrix. It's going to be sequence length, so number of tokens, by the embedding dimension, right? How many numbers we use to represent every word. And again, we're going to implement this in a bit, so you'll see more practically how it works out, but this is just to give you an idea. And we're saying the first word is 20% related to itself, 10% related to the second word, 40% related to the third word, and 30% related to the fourth word. So let's do the average. That's 0.2 times V1. V1 goes with the first word. It's the value projection of that first token. 0.1 goes with V2, 0.4 goes with V3, and 0.3 goes with V4. Right? So that's our setup. So we're just taking the weighted average of our value vectors based on our learned weights, right? Based on the weights. And that's our final output, right? We're just going to add these all things together. So the key idea, the input to attention, at least in the very first block of the transformer, and we're going to see what these are a little bit later, but the input to attention is X. Each token, each thing here, and for example, in queries and keys, each of these are a projection of the original data. It's basically some projection of our X's, right? And how many X's we have, in this case, we have 4 of them, right? We have a sequence of 4. So each of these are a projection of the X's. The output of attention is a weighted average of how that specific X was related to all the other time steps in your sequence. And that's the key idea. So the input, each token represents that time step, like the data of that time step or the projection of that data at that time step. But the output is a weighted average of how the data at that time step, the token at that time step, was related to all the other ones. And we weight them, add them together, and it produces an output. Now, one of the cool things about attention and transformers is that the input is the same as the output, like the shapes of our data. And we're going to see this in a bit. It makes it very, very simple to build transformer architectures. So we'll see that. But that's the key idea, right? So again, quick recap. we do QK transpose, we do the divide by the scaling factor and do a softmax, and it produces a matrix of how is every token related to every other token. And these relations are converted to probability vectors, but really they just add to 1, right? It's harder to interpret them as probability. You can just think about them as normalized proportions of how one word is related to all the other words. And then, once we know the weights, go ahead and weight your values, which is just another projection, producing a new context vector. Basically, this would be our C1, how the x1 was related to x1, x2, x3, x4. And then we'll have C2 will be the second row of how x2 was related to x1, x3, x, right, all the other ones. So that's the main idea. And so the output of this operation produces our context vectors. Now, we do have one key thing here, and this is to enforce causality. So I know we didn't really talk about bidirectional RNNs in the initial kind of implementation when we were looking at sequence classification and stuff. But you can imagine the regular RNN is how is this hidden state encodes xt plus 2 and the history, right? So this would be known as a causal model. And we leverage this causality when we went to generate text, right? When we were generating the Harry Potter text in our initial tutorial, we were leveraging that causality, right? We wanted to predict the next word given the history of the previous words, right? That's our generative task that we typically do, or causal generation. So we have our history here. And this is known as causality because ht plus 2 cannot look at the future time step. We can't look at xt plus 3 from ht plus 2. ht plus 2 can only look at the history. Now, a bidirectional RNN can look in both directions, and then it's valid. So there's two different types of RNNs, whether or not you want to work on a single direction, bidirectional. It kind of depends on the problem you're trying to solve. And we'll talk about when you would use which one in the future, in more detail in the future. So we'll look at that. But in this case, notice how when we're weighting stuff, let's take the third word, for example. So the third word is the third word is related 50% to the first word, 20% to the second word, 20% to itself, the third word, and 10% to the fourth word. Right? So let's make it a little bit bigger. So that's the relationship. But this means the third word can look at the fourth word. See how we're weighting it? So the context vector for the third word includes some information about V4, a word that came after it, which breaks causality, right? V3 should only be allowed to look at itself and its history, which is what makes it a causal attention mechanism. So we have to add in something known as a causal mask. And it's very simple. So we have our attention, right? Let's say we computed attention, but we need to do something with this top right triangle, right? We need to do something with it. And typically we just zero them out. We don't actually zero them out. You'll see practically how we do it a little bit later. We leverage the softmax to do it, but effectively we're zeroing this out. So we see that deep can only look at deep because it's the first word. Learning can look at the previous word deep and the current word learning. Is can look at deep, learning, and is. And fun can look at all the words because fun is at the end. So the only time we get to learn the entire sequence is when we get to the end of the sequence, right? The relation between all the words. And so decoder attention looks something like this. Notice we just zero out this top right triangle, but notice that we've renormalized the weights. So previously, right, in this attention mechanism, all of these weights had to add up to 1, right? That's the whole point of the softmax. We softmaxed it, so all these weights add up to 1, right? Every row adds up to 1. We still want every row to add up to 1, but we have to renormalize it with these. So see how it's 1, 0.3, 0.7 adds up to 1. And so now we have the first token can only look at V1. We zero out the effect of all future vectors. The second token can look at the first token and the second token, but we can't look at 3 and 4 because that's in the future, and so on and so forth, right? We just keep going. And so now that we have all of this set up, let's go ahead and implement a very simple example. So I've gone ahead and just done a little bit of a start here. So all we're going to need today is just torch, nn, and functional. So very simple. We're not going to be using any packages just yet. And I'm going to go ahead and define some random data. So my data is this is the typical sequence shape that we talked about if you're assuming batch first, but I will always assume batch first, so we're going to go with that. We have a batch size by the sequence length by the embedding dimension, right? So how many samples do we have? Because we want to train on batches. How long is every sample? So how many tokens or words are in every sample? And how many numbers do we want to represent every token from? And this is the typical output that our embedding matrix would produce, right? We're not going to be working with the embedding matrix right now. We're going to assume that we already have embedded text. That embedding matrix will show up in the future when we actually implement attention is all you need, right, for translation. So for now, we're going to go ahead and implement attention without any learnable parameters. So we're just going to take our data X. Notice that this whole thing we just talked about, projecting to queries, keys, and values, we don't actually need to do that. We can just do it on X. How is every token of X related to every other token of X? Weight it by itself and then produce the output, and it'll give you the same thing. Obviously, there's no learnable parameters there, so the results won't be nearly as good, but it should set a baseline for us to understand how we can implement some of these pieces of attention. So very simple. I'm going to call this a similarity matrix, so similarity. And this is going to be just following the formula. X at X dot transpose, and probably good to mention this actually. We've never actually looked at the transpose function before, so we're going to look at that now. We're going to look at X dot, so here's our data X, whatever it may be. If we do dot shape, we have 4 by 64, so batch by sequence length by embedding dim. But I need to do X transpose, so I need to do a 4 by 128 by 64. So the transpose, remember, will happen on the sequence and embedding dimension. So notice here, this is to compute our queries, or our attention matrix. It's the sequence by embedding times and embedding by sequence. So we have to flip those two, but the batch dimension should stay the same, right? The batch dimension is what we're parallelizing this operation over, so we don't need to worry about it. So we just need to flip these last two dimensions here. So we can go ahead and do that. We can do X dot transpose, and we can specify, I want to flip 1 and 2. So if we look at the shape now, we've effectively just flipped those. So there we go. And our similarity, so we can go back here, it's going to be X dot transpose, again, 1, 2. And it's going to be X at, or this is your shortcut. You could also use torch.matmul, but the at operator is just a shortcut for matrix multiplication. So we're multiplying a 4 by 64 by 128. That's our original X. And we're multiplying this by a 4 by 128 by 64, because we transposed it, right? And so this at operator will automatically, it'll parallelize over the batch. So for every single sample in the batch, if you imagine it like a loop, but obviously it's happening in parallel, for every single sample in the batch, we have a 64 by 128 times a 128 by 64, producing a, what we hope to be a 64 by 64. And we can check that. So we can do similarity dot shape, right? So we have a 64 by 64. So we had 64 tokens in the sequence, right? 64 tokens, which means this matrix encodes how is every token related by a dot product similarity. How is every token related to every other token, right? So it's 64 by 64 matrix, square matrix. So we're good to go there. But I do want to point something out. If we look at the similarity.var, if we look at the variance of this matrix, notice this is a very large number, right? This is a pretty large variance. And this is exactly why we have this normalization constant, right? It's basically to cool our logits, the raw outputs. You can think about it like a temperature parameter, basically. But the main idea is we want to reduce this variance. It's just too much, right? And the variance will scale with your embedding dimension. So the larger your embedding dimension, the larger your variance will become, right? So we just want to reduce this. So we will divide this by the square root of our embed dim 0.5. Right? We're going to divide by this. Now our variance is much smaller. Right, so we're basically, this is a temperature parameter. It makes softmax better. It makes our probabilities kind of more reasonable. You can just think about it like a temperature parameter. So there we go. So we have our similarity computed here, and this covers the first part, right? X transpose divided by the square root of our embedding dimension. But if we look at our similarity, and actually to make our life a little bit simpler, let's make the sequence lengths 6, right? Just so we can actually take a look at some of these matrices. If we look at similarity, right? If we take a look at similarity, let's make it even smaller, just so it's super clear. It is notice we have basically a batch dimension. So we have 4 samples, 1, 2, 3, 4. And each sample is represented by a 3 by 3 attention matrix. Because in this case, we only have 3 things in our sequence length. So we have a 3 by 3 attention matrix, right? Nothing crazy. And we have 4 of them, 1 for every sample. But what we want is for every row of our attention matrix, as we saw up here, we want every row to add up to 1. So when we do the weighted average with V, we're kind of weighting by some type of normalized probability, right? So how do we turn something from a vector to something that adds up to 1? Well, the softmax seems to be the obvious choice because we use it for everything else in neural networks. So we're going to go and apply the softmax. We're going to do dot, we're going to do similarity dot softmax. But if we just do softmax, it's going to throw an error, right? It needs a dimension on which we want to apply the softmax. We want to do it along the rows, so we're going to do dim equals -1. So now every single one of these rows will add up to 1, right? We want to do it along the rows. If we did dim equals, let's say if we did 1 instead of -1, so then it would do it along the columns. So actually, this is also the equivalent of dim equals 2, right? So dim equals 2. So 2 will do it along the rows. 1 would have done it along the columns, which is not what we want. And then 0 would have done it along the batch, which is also not what we want. So we want to do it along the rows for each of these attention matrices. So we have our softmax. And this now produces our attention matrix, right? So we can call this attention matrix, just like that. And then we can look at the attention matrix again. There we go. And last part of our formula, we need to weight it by our x, right? So that's the last step. We've computed this. Now we have our values. In our case, it's just x. And we know how is every x related to every other x. And so I want to weight how this x is related to all those other ones. So we get the weighted average of how this specific time step is related to the global context of all the other time steps. Right, so there we go. Obviously, there's no learning happening here because there's no learnable parameters, but it's the same principle, right? So we're going to go with it. So we have our attention matrix, and what we're going to do is just multiply it by x. And so this will give us our final output. So again, it's important to take a look at shapes real quick. So we can look at attention mat.shape and x.shape again. We're multiplying a 4 by 3 by 3, how is every token related to every other token, to our 4 by 3 by 128, basically embeddings for those tokens. And I'm just weighting up how is the token related to all the other ones? Well, I'm going to grab all those other ones and weight them accordingly and do the matrix multiplication. So again, this at operator will parallelize over the 4. And so we're really just doing a 3 by 3 multiplied by a 3 by 128, producing a final 3 by 128 output. And so this will be our output. And there we go. So like I mentioned, transformers, the input shape and the output shape is always the same. So we have a 4 by 3 by 128, right? 4 by 3 by 128 is what I passed in, and 4 by 3 by 128 is what comes out, right? Except the difference is here, each one of these 3 tokens here represents an embedding, right? For that time step. Like this is the embedding for time step 1, time step 2, time step 3, basically the word vectors, right? That pop out of our embedding matrix. Here, each time step represents how was embedding 1 related to all the other embeddings? How was embedding 2 related to all the other embeddings? How was embedding 3 related to all the other embeddings? And that's it, right? So we can now make this a little bit bigger, right? 64, but everything else stays the same. And this is attention, right? Just these couple lines of code implements one of the most important ideas in neural networks that powers almost every single architecture, state-of-the-art architecture out there today. It's used in speech, it's used in language, it's used in images, it's used in generative models, it's used in graphs, it's used everywhere. There is some type of attention mechanism being leveraged everywhere. But we still have something missing. There's no learnable parameters here, right? All we did is take a matrix and just perform the formula and ta-da, we have attention. But we need to introduce some learnable parameters, right? So we're going to go ahead and do that. So before we include learnable parameters, I do want to mention one thing. This has to do with linear layers on multidimensional tensors. And this is very simple. I think we've maybe talked about this before, but I do want to recap it. So let's say we have a linear layer with 10 inputs and 20 outputs. So we're used to doing rand is torch.rand with 10 inputs, or a batch size of, let's say, 4, and there's 10 inputs in this random tensor. And so then we do linear rand.shape, and there you go, right? It was a batch size of 4 with 10 inputs, and it produces, it takes in 10, it outputs 20, so there we go. We have 20 here. So it affects this last dimension. What if we have a multidimensional tensor? Because notice here, we don't have batch by something. We have a batch by sequence length by embedding dim. And what we want to do is project each one of these embedding dimensions independently, right? Each one of them independently to our queries, keys, and values. Well, let's go ahead and add that. Let's say we do a batch by sequence length by embedding dim, right? So 4 by 6 by 10. Now, technically, we could do this. We could do rand is equal to rand.reshape 4 times 6 by 10. So this produces, so what we have here is we have a batch size of 4. Each sample in the batch has 6 tokens, and each token is represented by 10, an embedding dim of 10. Well, that's the same as saying I have 24 tokens in total with 10, because the 4 and 6 are not really, we're not dealing with a sequence here. We want to just project every single token independently, right? Do a matrix multiplication. So why not just go ahead and flatten the 4 and 6? Now we have a 24 by 10. Now I can do my linear rand. That'll produce a 24 by 20. So I've taken every single one of our embedding vectors here, projected them to a vector of length 20 from the original vector of length 10. And then I can go ahead and just dot reshape back to 4 by 6 by, in this case, 20. So what did I just do? I took my tensor of batch by sequence length by embedding dim. Because this is a token-wise operation, so we don't really care about the sequence. We just want to apply the exact same linear projection on all the tokens independently. I can just go ahead and flatten them like this, 4 by 6. So the batch 4 by 6 is now our fake batch dimension, right? We went from a batch of 4 to technically a batch of 24 tokens with each token being represented with a vector of length 20. And once we have this, we can go ahead and pass it through a linear layer and then put it back, right? Put it back to the 4 by 6 by 20 in this case that we came up with. So this is effectively projecting each of these tokens independently and then putting it back to our sequence dimension. Well, luckily for you, we don't actually have to do this hassle. PyTorch will do that exact operation for you. So by default, this 10 expects the last dimension of our tensor to be the input tensor. So if this was 15, for example, this will throw an error saying, I cannot, so notice here, it actually did that flattening for you. It took the 4 and 6, flattened it to a 24, and it has a 15 here. So now it's trying to multiply a 24 by 15 to a 10 by 20, which obviously these are not matching things. We cannot do this matrix multiplication. If this is 10, we are good to go. It will do it for you, and it does it correctly. So exactly what I just described, but the linear layer in PyTorch automatically handles higher dimensional tensors for you. But again, just to keep in mind, a linear layer has no sequence information. It doesn't know about the other tokens. It's doing every single token independently. And we'll be talking about how transformer models have a mix of pointwise projections or token specific or individual token projections, and then the attention mechanism to kind of mesh together how those tokens are related to each other. We'll see kind of that in more detail later, but this is exactly how PyTorch deals with multidimensional tensors. It just expects that the final layer or the final dimension here matches our input. And so we're good to go there. So let's go ahead and add learnable parameters. So we're going to do class attention nn.Module. So we're going to write the simplest attention module ever. Self embedding dimension, right? So we have to pass this in as some information. And we're going to store it self.embed dim equals embedding dimension. And we'll have a def forward self and we're going to throw a pass in there, and we're going to create some random data. So torch.rand, we'll do a batch size of 4 by 64 by 128, just like we had. So this would be a embedding dimension. Sorry. We'll talk about that in a bit. This is a batch of 4, 64 tokens, and then each token is represented by a vector of length 128. So that means our attention is the attention mechanism with a embedding dimension equals 128. And there we go. So let's go ahead and pass rand into our attention. You're going to see that right here. So yeah, this has no backward hook because I never did the super.init. There we go. And we should see if we print x.shape here, we'll see we have our tensor. So step 1, we want to project each of these vectors here to our queries, keys, and values. So each of these tokens get individually projected to 3 different matrices, our query matrix, key matrix, and value matrix. So let's go ahead and create them. So right now, what we're going to do is, and just like we did in the example up here, our input, right? Our input and query are the same length. So if the input had an embedding dim of 128, so if our input was a 4 by 128, so we have 4 tokens in the sequence, and each token is represented by a vector of 128, then our query is also 4 by 128. We'll have 4 tokens, and each token is represented by a sequence of, or a embedding dim of length 128. The only difference is these tokens are just projections, some linear projection of our input sequence. So we're going to do that. So we're going to assume the embedding dim just stays the same. We'll see why we don't do that all the time in the future, but for now we're going to keep it simple. We're going to do query is nn.Linear, and it's going to take self.embed dim in and self.embed dim out, just like that. And our keys and values are identical. So we can call this query, key, and value. Oh. There we go. And so, just like I mentioned, we need to produce a q, k, and v. So q is self.query x, and we can print out q.shape. And let's print out x.shape as well. Notice they're the same, right? We passed in a 4 by 64 by 128. When we pass it into our query vector, it produces a 128. Now, if we didn't make this the same, let's say we made the input embed dim, but the output 14, for example, then our input has 128, our output is 14. So just, keep that in mind. But we're going from 128 to 128 right now, and we'll change that in the future, and you'll see why. So we have our query, but then we're going to also produce our keys and values. So k, v, and then this is going to be query, key, value. So we're providing the same input x, just 3 separate projections. And this is allowing us to do learnable parameters. Like we're doing dot product similarity, right? In this case, before we're doing it between the x and itself, now we're doing it between query and key. So the queries and values, the queries, keys, and values get an opportunity to learn what is the best vector to represent the embedding we're looking for, the time step we're looking for. The keys can learn what's the best vector for me to learn, or projection for me to learn to make these dot product relationships meaningful. And the values can learn, well, I'm going to be averaged up by these query, key, attention matrix. What's the best vector that I can be to make those weighted averages meaningful? Right? So that's the big idea. We have queries, keys, and values, and they're just 3 projections of the exact same vector. And we're going to go ahead and just do exactly what we did before. Our similarity is equal to, in this case, it'll be q at k dot transpose. We're going to transpose that dimension, and we're going to divide by self.embed dim and to the power square root, right? 0.5. And then attention is going to be similarity dot softmax. Axis is -1 or 2, right, along the last dimension. And then output is going to be attention at v. Turn output. And that gives us a attention mechanism, right? That is our final attention mechanism. So this is known as a single head of attention because we did this attention computation. So I hope this makes sense, right? So again, this looks is identical, right? We didn't do anything. We just added, instead of just doing this whole operation on x, why not do it on 3 learned projections of x? So these queries, keys, and values, and how we compute the dot product and how we weight things is all meaningful. Like it can learn the best queries and the best keys and the values, just like we talked about. So that's the setup, right? This basically is powering every language model out there. There's some more complication that we're going to be going into in just a bit, but this gives you the bare bones idea of the attention mechanism. Now, here's the thing I want you to think about. When we do the queries, keys, QK transpose, right? We learn how is every word related to every other word, right? That's this attention matrix here is representing exactly that, the relationship between every pair of words in our sentence. But you could probably imagine that words are related to each other in different ways. Like there isn't just one way words are related to each other. There could be many ways that words are related to each other. Language is a very complicated thing. It depends on context, it depends on syntax, it depends on your writing style. And words can mean all sorts of stuff in relation to other words, depending on what you're trying to express, right? So one attention matrix may not be sufficient to capture all those interesting interdependencies and interrelationships between your words. Right? And so that's a problem. So we've kind of bottlenecked ourselves here, saying that, oh, the words are related in this way, and that's it. And so multi-head attention tries to fix that. It says, well, instead of producing one attention matrix, why not produce 3 of them, or 10 of them, or however many you want, right? So there's a couple of caveats here. So I'm doing an example here where I have an embedding dimension of 9, right? And I want 3 heads of attention, which means I'm going to be computing 3 attention matrices. So notice here, what I do is previously we projected from embed dim to embed dim. So if our embedding dimension is 9, we would have just gone from 9 to 9, and that's it. So here we go. So we're going to go from 9, but instead of going to 9, we're going to go to 3. Because we've divided 9 divided by 3 is 3. So we're going to 3. So we're going from 9 to 3. So our QKV, or our initial data, had an embedding dimension of 9, but our queries, keys, and values will have an embedding dimension of 3 in this case. So we've just divided it, right? Just simple linear layers, nothing fancy is happening. We do exactly the same attention computation on everything. We'll be multiplying a sequence length by 3 times a 3 by sequence, sequence length by 3 times a 3 by sequence length, leading to our final sequence length by sequence length. It's just this dot product similarity was done on a smaller embedding dimension, right? So instead of doing the dot product on the entire embeddings, we're doing it on a kind of a compressed version of it with just 3. And so there we go. So, but other than that, nothing changes. It's still the same sequence length by sequence length embedding dimension. And then I do my sequence by sequence, and I multiply it by our sequence by 3 values. Okay, and it produces an output of sequence by 3. And I repeat this 3 times, right? I do 3 separate sets of projections. So we have our QKV for the first head, QKV for the second head, QKV for the third head, and each of them produce a unique attention matrix, but nothing changed. The operation is still the same as what we've looked at so far. And we multiply all of them by their unique values, whatever popped out of that, that head from that projection. But then we go ahead and concatenate them all together. So our final output, notice here, our final output is still the same shape as the initial output, except instead of doing 1 projection and producing a single output, we're doing 3 projections, each with an embedding dim of 3, and then concatenating them together to get back to the 9. The problem you have now, though, is, well, I have 3 separate heads of attention. So the model has learned interdependencies, and ideally a good model will learn different types of relations. So here I drew the same attention matrix 3 times. This would be a bad thing, right? If all the attention matrices are just learning the exact same thing, then there's no point of having multiple. You'd just be good with 1. So we're hoping that the model will learn to pick up different types of interdependencies between words through training. But regardless, once we compute this attention matrix, we compute our outputs, we concatenate them together. These concatenations don't know anything about each other, right? The blue output doesn't know about the orange and green, and and all the other combinations. So then we do a projection to kind of mesh that information together of, oh, how is all this information related to all this? So notice we have a embedding dim of 9, and we produce a weighted average to, or basically we do a linear layer to, create one homogeneous embedding that understands the relationships or the interrelationships between the heads. So we have two things happening here. We now have interrelationship between words, and then we have the interrelationship between the different heads of attention. So we're going to go ahead and implement this. It's standard practice, by the way, to make sure that your number of heads divides your embedding dimension evenly. So if your embedding dimension's 9, you wouldn't pick 5 heads because you couldn't evenly divide it. Typically, like for the bigger transformer stuff we'll be implementing later, we typically have a embedding dimension of 768 with 12 heads of attention, which means each head has a dimension of 64. So let's go ahead and implement this. We're going to implement it in 2 different ways. The first one is going to be the dumb way. That's not very efficient because we're going to have a for loop over the heads. We're going to be looping over the heads of attention, but any kind of looping operation is not parallelized, so it's slower. So we're going to be speeding it up with a parallelized operation of attention. But just to get the idea, we're going to start with the dumb way first. So we're going to call this class multi-head. Let's scroll down a little bit. Right? Multi-head attention, nn.Module, just like before. And all we're going to pass in, just like before, is self. We need to provide it the embedding dimension, right? So what is the embedding dimension? But we also need to provide it the number of heads that we want to compute on, right? So self.embeddDim equals embedding dimension, and self.numHeads equals numHeads. And so that produces our first set, right? All the information we need. We need a forward, self x, and then again we're going to do we're going to do rand is torch.randn for by, let's do a 64 by 128, and we're going to do a rand, or model is, or I guess attention is equal to multi-head attention. Now do notice that if we pick 1 for num heads, then that's just the attention we already did. But if we pick 2, then we'll be actually producing, multiple heads of attention. So let's go ahead and try this attention rand. Again, just like always, I forget the super.init. There we go. And we need to provide here the embedding dimensions 128. And for now, let's do 2 heads of attention. Right? We can make it bigger later, but for now, keep it simple. We're going to do 2 heads of attention. This means that each head will have a 64 embedding dim, right? Because we started with 128, we have 2 of them, so we divide, and we have each head will have a embedding dim of 64. We concatenate them back together, we'll be back to that 128. So let's go ahead and do this. So just like before, we're going to do self.headDim is equal to self.embeddDim integer division by self.numHead. Right, so this should produce head dim will be 64 in this case, and you could also throw an assertion at the top as a sanity check that, oh, embed dim is indeed divisible by num heads. Right, so there we go. And we're going to create something called self.multihead QKV. So we need, in this case, we have 3 heads of attention. Notice we have 3 sets of QKVs. We're going to have 2 heads of attention in what we're implementing right now. So we'll have 2 sets of QKVs. So that means we'll have 2 Qs, 2 Ks, 2 Vs. So we just need to go ahead and save them. So we're going to create a nn.Module list. I think we definitely saw this when implementing the resonance stuff. It's just a list. It's a regular list. It's just a PyTorch list that can go to GPUs and stuff too, and it looks nice when you print things out. So otherwise, it's just a regular list. And we're gonna do for head in in range num heads. Right. So we're gonna loop through. We're gonna do QKV proj is equal to nn.Module dict. So this is going to be a dictionary, and it's a module dict. I don't think we've seen this actually. It's just a regular dictionary. It's just a PyTorch dictionary, and inside this dictionary we provide it, just like every other dictionary, the keys and the values. Right. So we're gonna do. Here. We're gonna provide it a. We're gonna call this first one Q, and Q is gonna be a nn.Linear with self self.embedDim is the input, but self.headDim as the output. And that's what's different from before. Before we did embedDim to embedDim. Now we're doing embedDim to headDim, right? The dimension of every head. Oh, whoops. And then we're going to have a k. Again, nn.Linear self.embedDim to self.headDim. And then again, v. nn.Linear self.embedDim to self.headDim. So there's our QKV projection for this specific head. And then I can go and store self.multihead QKV.append QKV proj. And so we can print it out, right? Print self.multihead QKV. And we'll see that we have 2 module dicts, and each module dict has a 128 input, 64 output. If I decide to make my number of heads 16, then I have 128 output, and then 128 divided by 8, or 16 will give me 8. And notice I have 16 of them, because I have 16 heads of attention. So there we go. There's our setup, all the QKV matrices that we need. And now we can go ahead and do our forward pass. So we're going to create a intermediate variable here, or not intermediate, but a list, right? Heads out. It's going to be just an empty list, and we're going to store in here the output of every head. Because remember, we need out 1, out 2, out 3, store them up, and then we'll concatenate them at the end. So we're going to create a list to just store them in there. Now that we have that, we can do for head in self.multihead QKV. So we're going to loop through our module list, providing each head, and Q is going to be head, and just like we index a dictionary, right, we're going to pass it through our x, or we're going to pass x through our Q, and then we're going to have a K, we're going to have a V, so this is going to be K, V. Now that we've done the QKV, everything else is the same, but again, the difference here is that if we print Q.shape, and all the other ones being the same, it's down to a embedding dim of 8. So we started with 128. We're now down to 8. Let's put this back to 2, just so it stays simple. So we're down to 64, right? So there we go. Everything else is the same. So we can actually go up here and copy paste this part, right? So we can copy paste this, because computing the similarity, computing the output, computing everything is ready to go. All right, so now that we have this, our output, we can print the output.shape real quick, take a look, and let's make the numbers a little bit different. So it's going to be if we have 4 heads, 128 divided by 4 is 32. So this output has an embedding dim of 32, because we projected it to that, so that just makes sense. And we can then go onto headouts, headouts.append output. Right? So we're going to go ahead and store these. And so our final headouts is a list of these tensors. So our final output will then be headouts is equal to headouts, and we have to do torch cat. We're going to concatenate on our head outputs, and we're going to concatenate along the last dimension, right? Because we have basically a what do you call it? We have a batch by sequence length by 64 if we have 2 of them, and we have a second thing that's batch by sequence length by 64, and we just want to concatenate the 64 and 64 back together, or the last dimension, so we end up with a batch by sequence length by 128, right? So we're going to concatenate on the last dimension. And then we can print headouts.shape, and we'll see that we have a error. Okay, let's see here. Headouts does not exist. Oh, because I called it headout. So there we go. Let's change all of these to that. And we have a 4 by 64 by 128, because we've concatenated those heads back together. So that is this operation happening here. So we had our outputs in a list, out 1, out 2, out 3 was stored in a list, concatenate them together. But again, these concatenated tensors one head doesn't know about the other ones. So now we need to do a projection just to get everyone to get to know each other, right? So we have to mesh this information together. And so we can call this self.proj. And this is going to be nn.Linear, and it's going to take self.embeddDim, and it's going to output self.embeddDim, right? Because we want to keep the dimension the same. We just want all the heads to get to know each other. So again, like if we do remember, so this would be a 9 input, 9 output. So this first output here is going to be basically a weighted average of all of them. The second output here is going to be another weighted average of all of them based on the weights of the linear layer, right? Because it's just a regular linear layer. And so these outputs are a weighted average of how all the tokens in every head was related to each other, right? So we have that. Sorry, let me fix what I said. How all the embeddings for each token is related to each other, right? Because this is the token dimension. So this is the sequence length. This is the embedding dimension. And basically one word is being represented by 3 chunks of tokens. And we want those 3 chunks of embeddings. And we want those embeddings to get to know each other. So there we go. So I just want to make sure I'm clear. So we have our head outs. And so we can do out is self.proj head out, and we can return out. And we're good to go. Oh, looks like we have a bug, but let's do that first. Wow, I keep adding S's in random places, but okay, heads out, whatever. And there we go. So this is a implementation of multi-head attention. But the problem is this. Notice we're doing kind of this for looping nonsense through our QKB. We never want to do a for loop, right? For loops are always slower. We want to utilize the GPU by parallelizing this operation. And so we're going to create a more efficient implementation. So let's do a quick, this isn't really a review, you probably don't know this, but we need to talk about matrix multiplication on a, let's see. Actually, no, let's start here. So we actually already talked about this. Linear layers on multidimensional tensors. Basically, the linear layer will apply to the final shape. So I can just copy paste this in, and we can look at it again, right? We have a 5 by 10. We pass it into a 10 by 30. That produces a 5 by 30. But then we could have this like super high dimensional tensor with all these dimensions. As long as this is a 10 and this is a 10, then this will produce the same thing, but this 10 becomes a 30, right? So there we go. We have our linear layers on multidimensional tensors. Now the question is, can we pack our linear layers, right? So what I mean by this is we have a linear layer here that takes 9 inputs and produces 3 outputs for the Q, right? So we have 9 inputs, 3 outputs for this query vector. This one is 9 inputs, 3 outputs. And then this one's again 9 inputs, 3 outputs. Can we not just do 9 inputs, 9 outputs, and then chunk them after the fact, right? Like, why do them separately? We can do them all in one go. So what I mean by this is we can do our tensor, let's say is torch.randn, or rand, we'll have a batch size of 1, a sequence length of 8, and a embedding dim of 9. And our fully connected is nn.Linear 9 by, so before we were going to have a query vector, we're going to have a 9 by 3, but we'd have 3 different query vectors, each of them being 9 by 3, right? But instead of doing that, why not just have one linear layer that's 9 by 9 for now? And we're going to do Q is going to be fully connected, and we're going to pass our tensor through it. So Q.shape should not be any surprise. It's exactly what you think. But I want to do multi-head attention. So now I need to take this Q and do we need to do torch.chunk Q. We want to cut up Q into 3 chunks along the last dimension. So we want to cut this 9 up into 3 sets of 3. So you can see that cuts up that's our first chunk, that's our second chunk right here, and that's our third chunk. So we've cut, and notice it's a split backward, right? But it's still the same idea, just chunking it up. And just to give a general idea, right? Just a general idea of why this works is we have a data tensor that's S by 9, and we're multiplying it by a 9 by 9 linear layer, right? 9 input, 9 output. So this should produce a S by 9 output, right? It's S by 9 times a 9 by 9 will produce a S by 9. So nothing should feel uncertain here, right? Just regular matrix multiplication. But what we need for multi-head attention is really we're going to take our S by 9, right? And we're going to send this to a 9 by 3. We're going to send it to another 9 by 3. And then we're going to send it to another 9 by 3. And then each of these will produce a S by 3, an S by 3, and an S by 3. And then we can concatenate all this back together to a S by 9, just like I've described before. So the thing is, instead of having 3 separate 9 by 3 matrices, why not just have one big 9 by 9 matrix and cut it up? So how does matrix multiplication work? We want to multiply this row, the first row of S, by this column. And then we want to multiply this row by the second column. And then this row by the third column, right? So this is the first chunk of 3. And then we'll have another chunk of 3, and then we'll have another chunk of 3. So again, this matrix multiplication between this embedding vector and this chunk of 3 will produce this first 9 by 3. Then the matrix multiplication between, again, the same vector and the second chunk of 3, right? Sorry, drawing's terrible. Will produce the second chunk. And then again, we'll produce the third chunk. So it's the same matrix multiplication, right? But instead of having 3 separate 9 by 3 matrix multiplications, why not just pack these together into a single 9 by 9 and then chunk it after the fact, right? That's the big idea. So let's go ahead, and that's just this. So we can actually, so notice it returns a tuple of 3 things because there's 3 outputs. So we can say chunk 1, chunk 2, and chunk 3, right? So there we go. Last thing we need to look at is multidimensional matrix multiplication. So PyTorch, by default, will do the matrix multiplication on the last 2 dimensions. So there's 2 things that need to be true. The dimensions of the tensor, they need to have the same number of dimensions, and then the last 2 things have to be flipped. So let's take a look. So we can do A is equal to torch.rand 1 by 2 by 6 by 4. And then B is torch.rand 1 by 2 by 4 by 3. So first of all, for me to do this matrix multiplication, this 1 and 2 and this 1 and 2 have to be the same. So it needs to, we need to have the same number of dimensions here. This 6 by, so all we're really doing is independently for each one of these. So this will kind of do it just like the linear layer. Let's make these different numbers. Let's make these 5 by 2. Right, so this is going to make it such that A will become a, so our 5 by 2 by 6 by 4 will become a 10 by 6 by 4. And our 5 by 2 by 4 by 3 will become a 10 by 4 by 3. And exactly how we did matrix multiplication earlier, right, when we're doing these matrix multiplications up here on these higher dimensional tensors with three dimensions, we need to do exactly the same thing here. It's just PyTorch will automatically flatten everything except for the last 2. And I can multiply a 6 by 4 by a 4 by 3 tensor, no problem, right? I can multiply 6 because 6 by 4, the inner dimensions match, and it's parallelized over the 10. So each one of the things in the 10 will happen independently. So we have 10 independent 6 by 4 times 4 by 3 matrix multiplications happening. So I can do an A at B here with no problem, right? And it produces all these outputs. If there's a discrepancy, if this is like, let's say, let's make these 1 again. So that's what this output looks like. So we basically have 2 outputs, each as a 6 by 3. So we have 6 things and 3 columns. So each of them being 6 by 3. If there's a discrepancy, let's say the first thing is a 1 by 2 and the second thing is a 1 by 3, it's going to say an error. Hey, these things don't match. So the only things that have to match is the last 2 dimensions. And also, if these don't match, like this, for me to multiply matrices, this 4 has to match this. If these don't match, it's going to say, hey, I'm trying to multiply 2 by 4 by 2 by 5, and that's not going to work out, right? So there we go. Just high-level ideas of how PyTorch does some of its high-level tensor operations. Okay, so let's go ahead and parallelize the heads. You can read through this. It'll tell you exactly what we're about to do. So let's go ahead and do it. This requires a little bit of effort. So we're going to do self-attention, tension, encoder, nn.Module, def init, self, and just like before, we need an embed dim, we need a num heads, and we're also going to throw in some other stuff we didn't have before, just to make it more like an attention mechanism you're kind of likely to see online, proj p. And we'll talk about what these are in a bit, but these are just dropout. So we've talked about dropout. It's to help with overfitting. So we have that here. And so first we're going to do super.init. Didn't forget it this time. That's good. Probably forget it again, but it's fine. Just like before, self.embedDim is embedDim. Self.num heads is equal to num heads. And then our self.headDim will be self.embedDim divided by our headDim. So there we go. And we don't actually need this self right here, so there we go. Now we're going to call this attention is self-attention encoder. We're going to take a 64 in. Let's do 2 heads. And we'll just leave everything else as 0. Rand is torch.randn. Actually, we had a 128 here, so there we go. And we have a batch. Let's do 4 by a sequence length of 16 by a embedding dim of 128. So we can do attention rand. And we need our forward function, right? So we're going to do def forward self x. And we can print out x dot shape. And of course, something is wrong. HeadDim is not defined. Oh, sorry. This should be divided by num heads. There we go. Right, so that's our data. So step 1 is we need to, so instead of having a list of QKV dictionaries, we're going to have one big Q, one big K, one big V that contains all the weights, and we'll chunk it after the fact and cut it up. So let's go ahead and do this. We're going to do self.query. Query is nn.Linear embedDim to embedDim, right? And our keys and values will be identical, right? So key and value will be identical. Query key value. So everything's the same. We're also going to throw in here a self.attention drop. It is going to be nn.dropout, just a regular dropout layer with this dropout probability. So there we go. We also need a self.proj. The projection layer is nn.Linear. Just like before, right? Nothing new. It's going to take embedDim in. It's going to take embedDim out because this is going to get the heads to know each other, right? And then we're going to do self.proj drop is equal to nn.dropout proj p. So there we go. Nothing crazy. So we're going to go ahead. I'm going to first do q, and then we'll copy paste it afterwards. So we're going to do q is equal to self.qproj x. So nothing so far should be worrisome. This should make sense. What are we missing? Has no attribute q, because I called it query, not qproj. There we go. So we have our query right here, a 4 by 16 by 128. But I need to start cutting stuff up. So what we're going to do is it's this 128 that needs to be split into 2 sets of 64. So we can actually do that. We can do dot reshape. Actually, let's go ahead and store here. Batch size by sequence len by embedDim is equal to x.shape. Right, we're going to store that right there. And what we're going to do here is we have, so this is batch by sequence by embedDim, so that's no problem. So let's do batch by sequence len by embedDim, but this won't change anything, right? This is the same shape. What we want to do is take the embedDim and split it into the number of heads by the headDim. So we're going to do self dot num heads by self dot embed dim. So this is going to take this 128 and split it into two sets of 64. What did I miss? Batch size and sorry, not embed dim. This should be head dim. There we go. So I took, let's just keep this up here as reference the whole time. I took a 4 by 16 by 128 and I chunked it. I chunked the 128, our embedding dim, into two sets of 64. Right? So that's step one of doing our multi-head attention. Now, remember our attention computation is going to be between, so we currently have batch by sequence by heads by embedding dim. Our attention computation is between sequence by embedding dim times embedding dim by sequence, right, when we do the transpose in the future. So we need to take this head dimension and move it out of the way. So if we can reshape this from batch by sequence by head by embedding dim to batch by head by sequence by embedding dim, right? So we're going to move it out of the way, put the head dimension before the sequence. Then when we multiply this, our queries, right? So this will be our queries. And when we multiply it by our keys, which will look like embedding dim by sequence length, just like we talked about, the matrix multiplication is going to flatten batch and head first, and then do this multiplication independently. So that means our matrix multiplication operation is being parallelized not only over the batch, but also over the head, because we want every head of attention to be computed independently. One head should not see the other heads at this point in the code, right? That happens later in the projection. So that's the key idea. We want to take this head dimension here and move it out in front, exposing our sequence by embedding them. So the way to interpret this now is, instead of I have a batch size of this, each sample is this length, we have this many heads and this many, the embed dim for each of those heads. We instead think of it, okay, I have this many samples. For each sample, I've split it into this many heads of attention. And then each head has a sequence by embedding dim thing in it, right? So this is basically this right here. If we go back to our figure, this is this. So instead of having one big Q matrix like we had here, we now have 3 Q matrices, each being one small chunk. So this would be a 3 by 3, 3 heads by whatever. So, okay, good. So that should, I hope that's clear. We're just basically, reorganizing our thing. So let's go ahead and do that. So to do heads, sorry, let me refresh this real quick. To do our heads, we need, where are we? Here we go. Oh, what am I? Sorry, my bad, just being a little wonky. Okay, good. There we go. Sorry about that. So now we're going to have dot transpose. What do we want to transpose? We have 0, 1, 2, 3. We want to swap the S and the H, right? So we're going to transpose 1 and 2. And this will produce our exactly what we have. So we can get rid of all of this. And we have a 4 by 2 heads, and each head is 16 tokens, with each head's embedding dimension being 64. So that's our query. And now similarly, we're going to use this to create our keys, K and V, right? Because everything else stays the same, which makes this architecture surprisingly simple to implement, as long as you kind of work through some of these small nuances. So query, key, value. Okay, good. So we have the value right there, and we can delete, we don't need you anymore, and we can leave that for now. Okay, so there we go. We have our queries, keys, and the values all set up. Attention will be computed exactly like how we did before. So now we're going to do attention is going to be Q at K dot transpose. And again, K is a bash by sequence by num heads by embed dim. So we want to do a num heads by head dim times a head dim by num heads. Or sorry, that is incorrect. Let me just print it out. Q dot shape, K dot shape. Sorry about that. We have a 16 by 64, the sequence length by our head dim, and then we have a sequence length by our head dim. So we need to transpose this 16 and 64, so we're multiplying a sequence by embed dim times an embed dim times sequence by sequence, right? So we just need to flip it around. So we're going to do K dot transpose, and what do we want to transpose? We're going to transpose these last two dimensions. So 0, 1, we're going to transpose 2 and 3, or -2, -1, right? However you want to write it. So we can do transpose -2, -1. So the -2 is this dimension, -1 is this dimension. We're going to transpose those, and we're going to multiply it by self dot head dim to the power 0.5, right? Square root, just like before. So do notice one thing here. Now that our matrix multiplication is happening on an embedding dimension of 64, because every attention matrix is actually happening on this embedding dimension, we go ahead and do our scaling on the head dimension, not the original embedding. Did I do that correctly earlier? So this is actually incorrect. This should be head dim. My bad. This should be head dim, right? So because we're doing here, this QKV is happening, this QK transpose is happening on this head dimension, along the head dimension, not the full embedding dimension. So we want to scale by the embedding dimension of each head. So that's my bad. Okay. All right. So we have all of this ready to go. I'll fix that in my notebook later if it's wrong there as well. Attention. Good. So that's our attention, and we also need to do our attention is attention dot softmax, axis equals -1. Everything else is the same. So we can print attention dot shape here real quick, just so you can see. So we have now a batch by number of head dims and our attention matrix. So now we have two attention matrices, each that are 16 by 16. If I change my num heads to 4, now I have 4 attention matrices, each 16 by 16, right, between the sequence length. So we're good to go, right? That's our setup. But again, we want to make sure in each of these attention matrices, each row, right, adds up to 1. So we apply the softmax along the rows. So now that we have that, we have our attention. And this is where we do our attention is equal to self dot attention drop attention. So this is where we apply the dropout to our attention layer. This is just to make sure that the model's not overfitting. The same reason we always use dropout, so nothing crazy. And then we do attention. So again, if we print attention.shape and print v.shape, now we're at the end of our formula. We want to multiply a 4 by 4 by 16 by 16 by a 16 by 32. So this should give us a 16 by 32 output. So we can just directly multiply this because all of this is the same. So we can go ahead and do output is, or I can call it, let's call it x is equal to attention at v. Print x dot shape. And so here's our final output. Now that our output's like this, it's time for us to put this back how we found it, right? So what we have currently is a batch by number of heads by sequence length by embedding dim. What we want is batch by sequence length by embedding dim. So let's go ahead and transpose these two. So we're going to put this back to 4. So batch by sequence length by num heads by embed dim. So let's do that first. So x is equal to x dot transpose 1, 2. Print x dot shape. So this puts it back. So we're back to batch by sequence by num heads by embedding dim. Now remember, these context factors we just calculated are independent of the head dim because we parallelized it over the head dim like we talked about. So when I go ahead and flatten this, right, basically I'm taking a 4 by 32 matrix and flattening it into a single vector of length 128. That's effectively doing the same thing as the concatenation. Basically I have in this case, I have a 3 by 3. So I have 3 heads by 3 head dim on each one. So I have a 3 by 3 vector where the first 3 come from this, the second 3 come from this, the third 3 come from this. That's me taking a 3 by 3 matrix and flattening it to a vector of 9, giving me one vector of 9. So this flattening operation, in the way that we've done it, is equivalent to this concatenation operation as well. So, you know, it's just how you, it's however you want to do it. I'm sure there's a bunch of ways of actually doing this. We're just going with simple. So we're going to do dot reshape batch by batch size by sequence length by embed dim. Okay. And we're back to here. And so notice our input shape, the output shape, everything is the same. All of this effort we just did here is to simply parallelize the heads. Notice we no longer have a for loop, right? Over the heads, we were able to leverage GPU parallelism to do it correctly. And so we're good. And just like before, each head is independent. They don't know about each other. So now it's time to get them to know each other. So x is equal to self.proj x. And then x is equal to self.proj drop x, return x. So this is us doing the projection and the dropout, and we're good to go. We can print out the shape. And this is basically a full-fledged implementation of our attention mechanism. The only thing that's missing is sometimes you'll see a bias flag here. And so for some transformer architectures, they've seen that convergence is faster when these QKV projections don't have a bias. So it's just basically you're doing y equals wx. There's no plus b. So sometimes there will be another toggle right here. So you can try and see, does it work better with or without bias? But other than that, right, this is basically a full-fledged attention implementation, and one we'll be using quite a bit in the future. Okay, that is step one, right? So this gets us to where I think most people probably don't struggle with too much. It's the attention padding and stuff that makes this a little bit more annoying and complicated. So let's go ahead and talk about padding. So if you remember back to LSTMs, and this is very much a language specific problem, we want to train on batches, but sentences are of different sizes. On images, we have the perk of, we can just resize, right? Interpolate our image to the size that we want. With sentences, we can't do that. So when we did the LSTMs for classification, we had to add those additional pad tokens, right? And so in the LSTM, they just learn to ignore the pad tokens, so we don't worry about them too much. But when we're computing attention, the pad tokens will mess up a ton of stuff, right? So they'll mess it up, and we need to make sure we're really careful about this. And this is why if you go on Hugging Face or kind of any kind of transformer implementation, you'll see in the forward function, there's an option to pass in an attention mask. And that attention mask is specifically related to this padding concept. So let's kind of talk about what's going on. Let's say we have, so we have these, we're trying to bash these sentences, right? Deep learning is fun. Let's code, and we love pi. The problem is, let's code is shorter than everything else, and we love pi is shorter than this. So we need to pad the shorter sentences to the longest one. So we add these extra pad tokens. So let's just look at this last sentence, right? So we computed an attention matrix, right? On every single sample independently. So let's just look at what the attention matrix of we love pi pad would look like. So we have we love pi pad, we love pi pad. And we're computing how is we related to we related to love, we related to pi, ... right? We're computing every pair of computations just like we've done before. The problem is we are okay with learning. So the pad, remember, is just extra stuff we've added in. The pad token doesn't actually mean anything, right? It's just a filler. It's a gap. We don't care about it. We don't need it. So we have a little bit of effort here. So this pad token, also similarly, this V4 is the fourth token. This V4 is the pad token, right? It's the projection of the pad token, because the pad token will have its own embedding dimension, just like everything else. So if we want to draw it out real quick, you'll have something like, if there's 3 words, right, you'll have your embedding for the first word. That's word 1, word 2, word 3, and then you'll have your pad, right? Special pad token. You'll have the embedding for word 2, you'll have the embedding for word 3, but then we're going to have the special pad token embedding, right? It's just a filler embedding that exists just to fill out our matrices so we can actually batch our tensors. But this pad token is going to mess stuff up. So if we look at our attention matrix, let's pretend we actually have values here, right, in our pad token. Well, then we're learning how is we related to we, how is we related to love, how is we related to pi, and how is we related to pad. Do we really want to learn how is we related to pad? Pad is something we added in, right? We shouldn't be related to pad at all. There should be no relationship there because the pad token is just extra. We added that in just to fill out the batch. So we want to ignore how is we related to pad. We want to ignore how love is related to pad. We want to ignore how pi is related to pad. We don't care. So, but then there's the flip side. How about how pad is related to we? How is pad related to love? How is pad related to pi? This is fine. We don't really care. So remember that later on, these embeddings are going to have to contain some type of a positional information. We haven't talked about, what that is, but there's going to be some type of a positionalness embeddings kind of in these vectors that represent each of these tokens. I would assume, right? My best guess is that when we compute attention, we don't want to learn how words are related to the pad token because the pad token's extra. On the other hand, we do want to learn how the pad token is related to the other words because the model needs to learn that the pad token just kind of comes after the other words. So it's like positionally at the very end of the model. So it's just like a filler thing. You can ignore it. It doesn't matter. The pad token shouldn't affect anything. So effectively, in our attention matrix, we want to zero out the columns that go with every corresponding mask. And the reason this again works out is we are going to weight it, right? So 0.2 times V1 plus 0.1 times V2 plus 0.7 times V3 plus 0 times V4. And again, remember V4 goes with the corresponding pad token, right? Because the pad token is the fourth token. V4 is the fourth token's projection in our model. And so notice that we always zero out the V4 column, right? It's always zeroed out. So the V4 never has an effect on how words are related to other words. And this is how we will be doing our padding token. It's really just as simple as that. So we need to zero out the column corresponding to that. Now, how do we do this zero out operation? We do it kind of like this. So let's pretend our tokens are 10, 2, and pad, right? So these are my raw tokens, and I go ahead and create my attention matrix, right? I could create my attention matrix 7, -8, 6, -2, 2, 4, 1, 6, -2. And these are the raw outputs of that attention computation, right? These are the raw outputs before the softmax, before we perform the softmax, right? So the raw outputs of the model, of the QK transpose. The thing is that when I go to do my weighting of how is this vector, or when I multiply my QK transpose to my V, I have this extra pad token. So I will fall into the trap of I'm learning how we is related to the pad token, how love is related to the pad token. No, we want to zero these out. So we want to zero out this column. But we also want to make sure these probabilities add up to 1. So you could do it separately, or we can do it in one shot. So the trick is just doing softmax. So softmax, if you remember, so let's kind of look at this real quick. Let's say we have some 5, 6, and 11, right? Just random numbers. And what I want to do is zero this number, right? I want to convert this to 0, but I want to make sure that these sum to 1, right? These add to 1. So softmax, if you remember, is e to the power xi plus sum j equals 1 to n e to the xj, right? So in our case, this would be e to the power 5 divided by e to the 5 plus e to the 6 plus e to the 11. That would be this value here, softmax. And the next one will be e to the power 6 divided by the same denominator. And the next one will be e to the power 11 divided by the same denominator. And notice that when you add all these three things together, the sum of them will be 1. So it is a probability vector. But this does not answer the question of how do I zero this out? And the trick we use is why not fill it with a negative infinity? So what we're going to do is we're going to take our 5, 6, 11. And we know we want to zero out this last column. And we were going to repeat this operation, right? It's row by row, but I'm just drawing one of the rows here. You'd have more rows down here. I'm just doing the one. What if we went ahead and just filled it with a negative infinity, right? And there'll be more. Well, let's do our softmax again. Now we have e to the power 5 divided by e to the 5 plus e to the 6 plus e to the negative infinity. We'll have e to the power 6 divided by same denominator. And then we'll have e to the power negative infinity divided by same denominator. Well, what just happened? E to the power negative infinity, this is just 0. So that means this whole term, I mean, it's not 0, but it's approximately 0, right? E to the power of a really, really big negative number is basically 0. So this is 0. So that solves the first problem. Our output here, this last output is 0. Now notice here, we have an e to the negative infinity in the denominator. This is also 0. So all we're left with is e to the 5 over e to the 5 plus e to the 6. And then the next one will be e to the 6 divided by, again, e to the 5 plus e to the 6. Because this e to the negative infinity cancels out in both of them. So this term and this term that was there goes away. They're zeroed out. And these two things sum to 1, right? E to the 5 over e to the 5 plus e to the 6. E to the 6 over e to the 5 plus e to the 6. And then the last thing was just 0. This all sums to 1. And so this is how we will basically come up with e to the 5 over e to the 5 plus e to the 6, e to the 6 over e to the 5 plus e to the 6, 0. So this is how we're going to make sure these two things sum to 1, and this thing, or any column that has a pad token, is set to 0, right? Or, yeah, set to 0. That's the big idea. So nothing too crazy. I outlined this with some more detail here, so you can see that in a multidimensional tensor. I have a pad token here. That means I'm going to fill my 7 minus 8, yada, yada, yada. We're going to fill it with a negative infinity. When we do the softmax, that makes sure that we have zeros in this column and all the other rows add up to 1. And that's it. That's our main calculation happening here. So how do we add, when we add padding to our tokens, how do we do this, right? How do we actually, build something like this? And it's pretty simple. We produce something known as the padding mask. And this is I think where the confusion begins, because different implementations will define the padding mask different. They have different ways you pass it in. There's different ways. Everything is different. Like, everyone has a different way of doing it, but they're all equivalent. They're just different. So what I want to do is just show you how I typically, and I think this is how most, I think how Hugging Face and most places are doing it, but regardless, I'm doing it how I do it. And as long as you kind of understand this, then if you just read the documentations to the other one, it'll just make sense what's going on. So let's say we have these three sequences, right? A1, A2, A3, B1 through B4, C1 through C3. The problem is sequence 3 and sequence 1 is shorter than 2, so we need to add these additional pad tokens. So what I want to do is create a Boolean vector identifying in sequence 1, is it pad or not pad? So, or is it not a pad token, or is it a pad token? So we're saying the first three things in sequence 1 is not a pad token, and the fourth thing is a pad token. In the next one, all four things are not pad tokens, so they're all true. And in the next one, the first three things are not pad tokens, and the fourth one is a pad token, right? So that's how we're doing it. So true, false. In other implementations, they'll flip it. Like, they'll put a true where the pad is and a false where the pad isn't. And when we look at this flash attention a little bit later, I think that's what they do. So we just need to make sure we're consistent, but it's the same idea regardless. We have this Boolean vector here representing non-pad tokens or pad tokens. The other way to think about it is, what are the tokens we want to compute attention on? So those are the things that are true. Things that are true, we want attention, right? Attention is good. We want to compute the attention matrix. Anything that's false is something we don't want to compute the attention for. So we're going to zero it out. And so let's just take one of these things. So this will produce if we look up here again, this will produce so this is three things with a pad token, which looks exactly like this, right? Three things with a pad token. So when we compute our attention matrix, we're going to produce a 4x4 matrix, right? Because there's 4 tokens, even though only 3 of them are valid. We're going to produce a 4x4 matrix, and we want to zero out the fourth column, right? And the way we can do this is, why not just take our pad matrix and expand it out. So for example, notice that for sequence 1, it's true, 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 false, right? True, 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 false. And this is a length 4. I'm just going to take this true, true, false and repeat it. So it makes a true, 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 false, true, 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 false, true, 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 false. So this is that 4x4. Actually, no, there should be one more here. So let's, I'll just draw it out. I'll fix that later. We have a, yes, there should be one more there. It's my bad. So we have a true, 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 false. That's what we have. And in the end, we're going to have a 4x4 attention matrix, and we want to zero out this last one. So why not just repeat this true, true, false, or true, 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 false, 4 times. True, 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 false, and then true, 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 false. All right, we're going to just repeat it 4 times. And so now this is also a 4x4 vector. And anywhere where it's false, we can set them to negative infinity, right, before we do the softmax. So that's how we're gonna do it. We're gonna take our attention mask, identifying which tokens we want to compute attention on, which tokens we don't want to compute attention on. For each one of them, we're going to repeat them however many times in our sequence. So in this case, 4. Our sequence length, we're going to repeat it 4 times. And then we're going to use this 4x4 matrix as a mask on this 4x4 attention matrix to fill in wherever it's false with a negative infinity. And that's it. That's the main idea. So let's go ahead and do that. So yeah, so caveat, technically we don't need to do this, and with the it can get confusing, different functions for stuff. Yeah. So different places do it in different ways. And we'll see. We'll see how we do it in just a bit. So let's go ahead and do this. So I'm going to generate a fake tensor. So I've created a fake random attention, right? So this is an attention matrix. It's a sample of 1 with a 6x6, attention matrix. So we can look at ran attention, and there we go. This is my 6x6 attention matrix of how things relate to each, and obviously there should be a torch.softmax. Actually, no, we don't want to do a softmax just yet. Yeah, softmax comes at the end. So these would be like the raw outputs of our model, right? So there we go, our 6x6. We now want to fill in our attention mask. We want to notice here we have 0s here and 1s here. So if we look at our attention mask, the last 2 things are false and the first 4 things are true. So we don't want to compute attention here, meaning we want to zero out. These last 2 columns, and there's 2 ways of doing this. PyTorch will automatically broadcast. Okay, so there's 2 ways of doing this. Let's do both of them. So method 1, right? We're gonna do method 1. And again, this is where confused instructions show up because everyone does it in a different way. We're gonna do attention mask is equal to attention mask dot unsqueeze 1. So if we print attention mask dot shape and rand attention dot shape, notice we went to we have a 1 by 1 by 6, so our attention mask. Let's also print this out here. Print attention mask. Okay. Oh. There we go. Dot shape. Okay. So our original attention mask. So our attention mask, when we provide it to our model, will be batch size by sequence length, right? So it's going to be 1. In this case, it's a batch of 1, so 1 sample with a sequence length of 6. If we had 10 samples, then it'd be a 10 by 6, right? So whatever it may be. But we have 1 by 6. And but our random attention is 1 by 6 by 6. So notice that. So we basically need to add an extra dummy dimension in here, a 1. So we can broadcast. So we went from 1 by 6 to 1 by 1 by 6. So we've just added a dummy tensor in here. So we have a batch size of 1, and then we have a 1 by 6 right here. And this 1 here will broadcast over this 6 dimension automatically. So it will automatically do it for us. So if we go ahead and do attention mask, or actually we're going to do rand attention dot masked fill. So this is a function that is built in, and we want to fill in with a infinity, right? So inf. And our Boolean mask is going to be the attention mask. So there we go. Now notice one thing here. It actually fills in. So we have these true here and false here. This will fill in where it's true. So we just need to flip it. So our attention mask was true and then false. We need to make it false and then true. So we could have actually done that to begin with, right? We could set it up that way, or we can just add a little Boolean flip right here. And there we go. We have now converted our last two columns to infinity. So when we do the softmax, so if we do torch.softmax along the last dimension, axis equals -1. Oh, did I make a mistake? Oh, wait. Yeah. Okay, no. Shouldn't be negative. It shouldn't be. It should be negative infinity. There we go. Yeah. So now that when we do torch.softmax, again, torch.softmax, axis is -1, we should get zeros on these columns and everything else adds up to 1, just like how we talked about. But the key idea here is my attention mask, right, is in the shape, attention mask is in the shape of 1 by 6. Or sorry, 1 by 1 by 6. So it's batch by our sequence dimension that we'll broadcast over, and then our sequence dimension, right? So there we go. That's how it works. Now the thing is that this is how we can do it. I think this is how I end up doing it. I can't remember off the top of my head, but we'll see. So regardless, we have this. When we do flash attention a little bit later, it doesn't want it this way. It explicitly wants if our attention, so if we do, let's comment all U out. Let's comment out U. So if you look at our attention mask.shape and our rand attention.shape, if our rand attention is 1 by 6 by 6, flash attention explicitly wants our attention mask to also be 1 by 6 by 6 because it won't automatically broadcast. So we just need to make sure that we make sure it'll be the same thing. It's just we need to manually make this 1 by 6 by 6 rather than doing a 1 by 1 by 6 and letting PyTorch broadcast it. So to do it this way, we just need to do attention mask is equal to attention mask dot unsqueeze 0 or 1, it doesn't matter, just to add that extra dimension. Actually, no, it does matter. So it'll be 1. So print attention mask dot shape. So there we go. So we have a 1 by 1 by 6 right here. And then we're just going to repeat this 6 times. So we're going to do dot repeat. We're going to repeat the first dimension 1 time because we don't need to change it. We're going to repeat the second dimension 6 times because we want 6 copies of it. And then we're going to repeat the last dimension 1 time because we don't want to change it again. Right? So now if we print out attention mask, it'll look exactly like what you think. It's exactly the same true, 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 false, false tensor, just repeated 6 times. So now this is a 6 by 6 matrix that can be directly placed on top of our attention matrix and perform the masking and whatnot. So again, nothing really changed. So again, we can just do this right here, and it gives us it'll be the same results, right? Same results. It'll fill these negative infinities. So when we take the softmax, it will convert them to 0. So this is how we do our attention masking. But this is attention masking assuming, remember, it's a batch by sequence by sequence. That's our attention shape. What if we have a head dimension, right? We really have a batch size by sequence length, or batch size by head dimension by sequence, right? We have multiple attention matrices. So let's go ahead and do that. So we're going to expand this out a little. We're going to do rand attention is going to be torch.rand, batch size of 1, just to keep it simple. But we're going to do 2 heads of attention and then a 6 by 6, right? So each head of attention is now a 6 by 6. Now, the thing is that we may have multiple heads of attention, but each head has the same mask, right? These 6 tokens are the same 6 tokens. We're just computing different attention heads, but it's the same token. So in each head, the last 2 tokens are always the pad token, no matter what. So we can go ahead and basically repeat this just the way we did it. But now we have to add an extra dimension in again. So we're going to do attention mask dot shape down here so we can see it. And so we're going to do, we have before, we added a unsqueezed 0 here to add in that extra dimension, right? Just so we can match our, this unsqueezed 0 here is to create the batch dimension. So this is batch by n, so ignore this. That'll come later when we actually build it. But this unsqueezed 1 here, right, adds in that dummy dimension, that extra dimension in the middle. So if we do attention mask dot unsqueeze 1, and unsqueeze will, and we want to set this equals to that. It adds in an extra dummy dimension here. If you don't know what unsqueeze is, if you do -1 actually, it'll add a extra dummy dimension at the end. If you add a 0, it'll add an extra dummy dimension at the beginning, but you can't tell because they're both 1. If you do it 1, then it'll add it in the middle, which is what we want, right? Because we have a 1/6 attention mask, and we have a 1/6/6 attention computation, right? So we need to add in an extra dummy dimension for that middle 6, right? For that 1/6/6. But in this case, we have another dummy dimension. We have this extra 2 here as well. So we're going to unsqueeze a second time. And now we have 2 dummy dimensions, one for the heads to broadcast over, and then another one to broadcast over the sequence length for the queries, right? So there we go. We have our attention mask. And just like we did, nothing else changes. We do ran attention. So if we look at that, we have 2 heads of attention. So we have 2 attention blocks, each are 6x6. We have our attention mask, which looks like this, right? And we're going to go ahead and do our masked fill. So dot masked fill attention mask. And we want to fill it with negative, or actually we can do float negative infinity, just like that. And we need to flip the, Boolean, so we're doing true. And so notice that we have masked out both of the last columns in both heads. Because again, in both attention heads, they're the same. These are both pad tokens. It doesn't matter which attention we're in. The last two time steps are still pad tokens. So now that we've gotten all this set up and we've pieced a lot of this together, it is now time to do our, let's see. Right, so the last method, right? Again, method 2. What if we need to manually create the attention mask, right? So again, in the case of flash attention in the future, flash attention expects the attention mask to be in the same shape as everything else. I think flash attention, I think flash attention will broadcast over the head dimension by itself, but it needs that sequence by sequence. So what we're going to do is attention mask is equal to attention mask dot reshape, or no, repeat. And remember, this is right now a 1/1/1/6, right? That's the dimension. So we're going to leave this as a 1/1. We're going to repeat 6 times on that last one, and then leave this as 1. So print attention mask. And there we go. We have all of this. This should look very familiar. If we had repeated on the head dimension as well, then it looks exactly like what you'd expect. 2 heads of attention. We're canceling out, we're setting these last 2 columns to false. Nothing crazy, right? So this should just play with it a little bit. And if you do it yourself just a little bit and just play with the tensors, it'll kind of start to become immediately obvious what's going on. But flash attention actually will broadcast over the head dimension, I believe. So technically this is all we're going to have to do, but either way, this just sets it up. So this is how we will be doing our multi-head attention with masking. So let's go ahead and copy our attention mechanism that we already made up here. Oh, made it too big. Let's copy all of you. Oh, that's the wrong one. Let's do the efficient one. This one right here. We're going to copy all of you. But we're going to add in the extra step of attention masking, right? Padding mask. So instead of just passing in X, we're going to pass in one more piece of information. We're going to pass in an attention mask. And by default, we're just going to set it to none, right? So if we don't have an attention mask, then we won't be doing any of these operations. So this operation applies exactly where you think. We compute the attention, And then on the columns of attention in every single head that we had a pad token, where the pad token is indicated by the attention mask, convert them to minus infinity. So when we do the softmax, it becomes, 0 and normalizes everything else. So the extra new code we're writing is going to be right here. So I'll just block it out. Right? This is the new stuff that we're going to be adding. So we're going to do if attention mask is not none. And actually, this would probably be helpful to have some dummy tensors that we can pass through. So what I'm going to do is create some data, and I'm going to do it like this. Let's call this self-attention. Okay, so self-attention, there we go. All right, so what I've done is I've created a list here called sequence length 3, 5, 4, right? And my embedding dimension, I want 9 and I want 3 heads, right? Keep this simple. And so I go ahead and create a random tensor in the shape of my data, right? Batch by sequence length by embedding dim. And so there's no problem there. But I've also gone ahead and created my mask. So this means that if there's 3 things in the first sequence, 5 things in the second sequence, and 4 things in the third sequence, I need to add 2 extra pad tokens to the first sequence to get it to 5. The second thing is already the max length, so we don't worry about that. And the thing that's 4, we just need to add 1 more pad token to it. So I just did that by just doing list comprehension and using the RNN.pad sequence and using 0 as my padding value and converting to Boolean. So then we have falses here and trues everywhere else. So this should look exactly like what we've done, except the example we looked at so far, we were looking at just a batch size of 1, right? We're just doing batch sizes of 1. Now we have a batch size of 3 because we have 3 different attention masks, telling us in every single sample which tokens do we want to compute attention on? Those are these. And which ones do we not want to compute attention on? That's these. So what we do is now pass into our model this. So we're going to do output is equal to A, rand, and attention, masks, right? We're going to pass these in. And so now if attention mask is not none, we should get print attention mask, right? Let's close that parenthesis, and you should see that right here, right? That's this, our mask, so nothing crazy. It's time to now apply it. And again, there's a bunch of ways you can do this. We can broadcast it, we can reshape it exactly how we need it. It's completely up to us, but I'm just gonna do it the easy way. How I normally do it is, honestly, it's just a preference thing. Attention mask is equal to attention mask dot unsqueeze, and let's print out the attention mask dot shape just so we can see this happen in real time. And I'll also print it out right here so we have a comparison case. So by default, right, our attention mask is a 3 by 5, batch size of 3, 5 tokens, and these are Boolean indicating trues and false. So what I need to do first is unsqueeze, and we're going to add an extra dimension at 1. So now we have a batch size by, remember, this is going to create a sequence length by sequence length attention mask, or attention matrix, right? Sequence length by sequence length. So this can be converted to a 3 by 5 by 5, and we'd be good to go. Except we have multiple heads of attention. So really, we need another dummy dimension here to broadcast over. So we're going to do unsqueeze, and then again, dot unsqueeze 1. And so now we have a 3 by 1 by 1 by 5. And if we take a look at our print attention.shape, right, we should see that our mask is 3 by 1 by 1 by 5. Our tensor, our attention tensor, is 3 by 3 by 5 by 5, right? So this is good to go. We can broadcast over these 2 dimensions, and it'll fill in trues and false, or basically minus infinity wherever it's going to be false when you flip it, right? When we use the Boolean flip. So this is good to go. Or if we want to make it closer to how the flash attention expects it, we can do dot repeat. 1 and 1 is fine, right? So this will say a batch size of 3, no need to repeat there. This will say 1 because flash attention will already broadcast over the head dimension for you, so we don't worry about it. But 1 and 5, we need to make this a 5 by 5, right? Because our full attention matrix is a 5 by 5. So we just need to repeat this 5 times. So In this case, we're going to do a 1 by 1. And then we're going to repeat its sequence length a number of times. In this case, sequence length just happens to be 5. And then the last thing stays 1. And so our final thing will be a 3 by 1 by 5 by 5 and a 3 by 3 by 5 by 5. So if we print out the attention mask, and let's just print out the attention mask for the first sample, just to keep it clean, and the attention for the first sample. So we have a, let's see, attention mask 0. Yes, yeah. So we actually, okay, so we have here 3 heads of attention, 1, 2, 3. And here's my mask, identifying that the last 2 columns of all of the heads of attention, so it'll broadcast across the heads of attention, need to be masked out, right? Set to -infinity. And so now that we have this, we can go ahead and do attention mask dot masked, or sorry, it's going to be attention dot masked fill. And also this masked fill underscore is a in-place operation, so it'll directly fill it. Or we can do attention is equal to attention dot masked fill. We want to fill it with the inverse of our attention mask because we want it to fill where it's false. We want negative infinities to go there. Again, you could have just done it as like, you could just look at true and false to begin with. There's, again, you can do this however you want, and that's what makes this a little bit more confusing than it really needs to be. So let's take a look. In the first sample, the last 2 columns in each head are -infinity. We've converted them to -infinity. In the second sample, all 3 heads, nothing has changed because nothing here is a pad token. In the third sample, all 3 heads, the last token is converted to -infinity, or the last column, because, again, it is a mask token. And that sets it up. So now when we go ahead and do our softmax, right here, print attention, right? We have zeros in these columns, nothing changes here, and then zeros in this last column. And that's exactly what we have. This is basically our self-attention with a padding mask incorporated. Again, adding this sequence length or this repeat here is optional. PyTorch by default will go ahead and do that broadcasting for you. Again, we can print attention, right? It went ahead and did that broadcasting for you already. It's just when we go to use flash attention, I keep mentioning flash attention, by the way. We're going to talk about it in more detail a little bit later. But for now, right, this is just to get you kind of knowing that flash attention kind of expects the attention mask in this shape. So that's what I'm going with, just to maintain some level of consistency in what we're trying to do here. Great. So now we have, okay, so let's do a high level recap. What have we talked about? We've talked about a single head of attention, how we expand that to multi-headed attention. Then we talked about how we can do it more efficiently by parallelizing the heads of attention. Then we talked about how padding masks, or how we need to incorporate a padding mask so our model is not learning how tokens are related to pad tokens, because the pad tokens don't mean anything. They're just there to fill out the matrix. But we do want to compute how the pad token is related to the words, because the model needs to learn that, hey, the pad tokens just kind of exist at the end, so it's mostly just positional information. But how the words are related to the pad token should not matter, right? The words have nothing to do with the pad token because the pad token was never there to begin with. It's just a filler. We go ahead and fill out our, create our attention matrix. We can do it for our masked, we can fill our attention matrix with negative infinities for a single head of attention. We can then do it for then we can do it for multiple heads of attention. And then we can just take the code we already wrote for self-attention and just add the extra masking strategy in case the attention mask is passed in. So we're good to go here. We have padding mask done. We have one other kind of mask though, and this is our causal masking. So causal masking is just like we talked about. We want to make sure that every token can only pay attention to itself and previous time steps. So you can't look into the future. The word learning can only look at learning and deep, because isn't fun is in the future, and that would break causality. And so to do causal masking, it looks exactly like what we've done before, except now we want to fill the top right triangle with a negative infinity. For the same reason we've done this before. We fill the top right triangle with negative infinity, and by doing so, we then convert this top right triangle to zeros, which looks exactly like what we have here, right? Convert the top right triangle to zeros. So when we do our attention times v, any token that's after the time step we're on is just zeroed out. So we don't have to think about it, right? It has no effect, and it maintains causality. So let's go ahead and talk about how we can do this. So this should be very familiar. Nothing changed. You can look through this math. This math is identical to everything we did. It's just instead of filling columns with negative infinity like we did, we want to fill like this top right triangle with negative infinity. Nothing else changes. So I'm going to just go ahead and copy this little piece here to create the data. There we go. Yes. Okay. Good. Yeah. So there's actually one other thing. So we'll talk about that in just a bit. So PyTorch has a nice little function called torch.trill. So in torch.trill, you just provide it torch. So for example, ones is just a square matrix, right? It's just a square matrix of ones. And if we do torch.trill ones, it will automatically fill the top right triangle basically with zeros. Just that's what it does. So, as simple as that. And then we can go ahead and convert this to a Boolean. So we have a true false, just like we had. So we have true where we want to compute attention and false where we don't want to compute attention. Right? So that's the big idea. We have false now over here. And so again, exactly for the same reason we did attention padding, nothing has changed. All the math and everything has stayed the same. So we're going to go ahead and create, this is now our causal mask that we're going to leverage to do our causal masking, right? So there we go. This is what we're going to fill in. But there's one other thing. We could have a causal mask and a padding token. For example, right? It's probably easiest just to draw this out. Let's say our data, right? Because data, we may have had a padding. So we have word 1, word 2, word 3, and then a pad, and then a pad. Right? That's what we could have. So that means, let's say, so this has 5 things in it. So it's going to create a 5 by 5 matrix, 5 by 5 matrix, 5 by 5 attention matrix. And what we want is, let's say A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Right? So there we go. These are the values we want to compute attention on. And everything else should be 3, 4, 1, 2, 3, 1, 2, 1. Everything in this top right triangle should be zeroed out. Except one thing. This token here and this token here, right? These columns refer to these pad tokens, which means these values here as well should be masked out. So that means we're really just left with this like trapezoid piece of data, right? That's what we have left. So you need to zero. So we have 2 masks going on now. We have the causal mask, but because of our padding tokens, we technically should pad these out as well, or mask these out as well. We don't care about them. We don't want to learn how the 5th token is related to N and O, because N and O are pad tokens. There is no relationship between them. And so in this case, we need to have both a causal mask and an attention mask. And that's easy enough, right? So we just need to stack masks. So this is our first mask. Now let's pretend I'm going to create this padding mask right here. Let's copy paste this in, right? So let's pretend this is our padding mask. And we can look at our padding mask. It's nothing crazy, right? It's exactly what we did before. Basically, I have the last 4 things set to false, like we don't want to compute attention on them, which means the last 4 columns are set to false. And we can go ahead and then fill in our causal mask is equal to causal mask dot mask fill. Flip our padding mask just like we did before. Because wherever this padding mask is false, so when you flip it, wherever it's true, we want to fill it with zeros. And so now our causal mask looks like this. So we have causal attention until we get to these last 4 columns, in which case the entire columns are blocked out. So really the causal attention is happening up to here, and everything else is pad tokens, right? These are all pad tokens. We don't really care about them. The model will learn. So we have, in this case, 1, 2, 3, 4. So we have 1, 2, 3, 4. So we have 1, 2, 3, 4 pad tokens. That's going to learn how are these pad tokens related to these words, right? To the actual first 4 words of the data. And this is again going to basically tell the model, hey, these pad tokens kind of come after. It's probably just positional information. But these first 4 tokens will only learn how they're related to themselves and previous tokens, and never any pad tokens, right? We never will have any pad tokens because we masked them out. So we're just stacking different types of masking procedures here, but it's still a mask, right? Nothing has changed. It's just we have this extra little causal bit added onto it as well. So how do we add this into our model? Well, nothing crazy. We're just going to go ahead. We're going to copy all of you, stick you right here. So same implementation as before, but we're going to add a flag. Do we want to do, let's say, causal equals true, right? Do we want, or actually, by default, typically causal set to false. So do we want to do causal? And we're going to stick in here a self-attention. We're going to say causal equals true, right? So nothing has changed yet. So we're going to do self.causal equals causal. Just set it causal. Just set it as a class variable. And we can go ahead and update our code. So we're going to come back to this chunk here in a bit. So I'm going to comment it out for now. We're going to do if causal, right? If causal, then we can do ones. So this is just the code we had before. Ones, right, is just this. So we're just going to copy this in, create a matrix of ones, and create our causal mask. As simple as that. Now, one thing to keep in mind is when we create a tensor like this, we want to make sure that if we're training on a GPU, for example, when we create a tensor, this is actually created on the CPU. So if we want to create it on the GPU, we need to specify that we want to do it on the GPU. We know that QKV, like all X, QKV, attention, all of this stuff's happening on the GPU. So we can just make sure that the device here is set to attention.device. So this will create our ones on the GPU, and then there's no problem. So this creates our attention mask. Right here, the causal mask, sorry, the not attention mask, the causal mask. And just like before, causal mask is equal to causal mask dot reshape. And we're going to add in extra dimensions, and we're going to reshape it to sequence len by sequence len. Right, so let's see here. So let's close you. And if causal, actually, you're right. Yep, this should be if self.causal, right? Because it's a class variable. And we can then print in here, print causal mask. And you will see that this causal mask has been created like this, right? Nothing crazy. The problem with the previous causal mask was that it was sequence by sequence len, but we need we need to broadcast over the batch dimension, and we need to broadcast over the head dimension. We could have also done this as .unsqueeze 0, .unsqueeze 0, right? Just adding in some extra dummy dimensions. Both are valid methods. It's just it's a preference thing. It doesn't really matter. So that's our causal mask. Now, if our attention mask is not none, so now we have a causal mask, but we've also passed in some attention mask information right here. Then we have to do the rest of this stuff, right? So if attention mask is not none, so there we go. We're going to do this, delete you. If the attention mask is not none, then we create our attention mask right here. And we can do a little bit more effort. So let's see here. So we've created our attention mask. It's going to be in sequence length by 1. We're not going to do you just yet. So now we can print attention mask.shape and print causal mask.shape, right? So this is just keeping everything the same. We have a 3 by 1 by 5 by 5, and then our causal mask is a 1 by 1 by 5 by 5 Everything is fine, but again, if we want to make these as similar as possible, we can repeat the causal mask batch number of times to make this a 3 by 1 by 1 by 5. You don't have to, right? It'll broadcast on its own, but we'll just do it just to do it. So our causal mask is going to be causal mask.repeat. And again, we want to go from 1 by 1 by 5 by 5 to a 3 by 1 by 5 by 5. So we want to repeat this one 3 times and then leave everything else the same. So we already know the batch size, that's this. So we're going to repeat this batch size number of times, but then 1 by 1 by 1. And then our final causal mask is going to be causal mask dot is equal to causal mask dot masked fill. And we'll just invert the attention mask just like we did before. And we can stick in here a false, because remember, this attention mask is already a Boolean. So we'll just fill it with a false, and we're good to go. So print causal mask. Sorry, I meant the causal mask is already Boolean. So if we're going to fill it in, then I guess they're both Boolean. It doesn't really matter. Oh, I spelled it wrong. So there we go. Here's our causal mask. So notice that in the first sample, we have the last 2 columns as set to, again, we don't want to compute attention on it. So we completely block out the last 2 columns. But every other column, we have this causal, the right triangle causal happening. And in the second one, there's nothing there is no pad token because it's the longest sequence. So this is just a regular causal attention. And then here, we only have the last thing as a pad token. So we basically block out the last one and we do causal attention everywhere else. And so now that we have all of this set up, this creates our causal mask. And we can just go ahead and do attention is equal to attention dot masked fill. And then we will have a causal mask. There we go. Now this actually isn't the best implementation. This should actually just be a causal self attention. Notice that if I pass in an attention mask, but I'm not causal, then this chunk actually won't run, and that's fine. We're gonna write a better version of this anyway in the future. That's just my bad, but yes, so this should be good to go. Maybe a better way to implement this actually would be to stick if attention mask is not none, then we do all this stuff with the attention mask. And then we will have another one right here. And we can do if attention mask is not none, then we're going to go ahead and update the causal mask with that new attention mask. This is more accurate actually, so we'll just do that. And then we do attention mask is dot masked fill. I guess attention mask. It's fine. We're gonna write a better version of this anyway. You get the idea. So we're basically updating the mask over and over again, and this should be fine. I can fix that code later. Yeah, it's just my if else is kind of a little wonky, but that's fine. If this was causal, then this would have worked. So this is fine. Okay, so we have talked again. Now we've covered attention and our causal attention and everything else. So now let's just kind of recap ourselves based on what we're trying to do. So in our attention is all you need paper, let me pull that figure up again. All is all you need. Here we go. Okay, in this figure here, right, we have now implemented multi-head attention and we have implemented masked multi-head attention. Right, so these 2 blocks are now complete. This is your self-attention. This is your causal attention. Now we need to implement our multi-head cross-attention. So cross-attention is exactly like self-attention. There's nothing new happening. The only difference is, in self-attention, we are interested in how our English, like let's say we're doing language generation or language classification. We're interested in how every word in my sentence is related to every other word in my sentence. And that's self-attention, right? How am I related to everything in myself? Cross-attention asks, how am I related to something else? And this is used all over the place. So in the case of language translation, I think it makes it the clearest. In language translation, we want to go from English to French, let's say. So that's the example we'll be training later. We're going to train something that can take English and translate it to French. Well, in language translation, we need to learn how is the English related to the English and how is the French related to the French. But we also need to learn how is the English related to the French. So that's cross-attention. Cross-attention is when you're computing basically the change in modality, right? You're going from one thing to another thing and how they're related to each other. Cross-attention shows up in all sorts of places, like when you're doing, when we implement diffusion models later, or generative models later, there are text conditional generative diffusion models. So that means we give the model some text and it generates a picture that corresponds to it. How does it do that? It does it through cross-attention. It learns how is the picture related to the text. So you're kind of combining different modalities. So cross-attention is super important, shows up all over the place, and we're going to need it for language translation because we need to learn how to convert the English to the French, right? So let's go ahead and talk a little bit about how we do this. There's a little bit of a change in mindset, I guess. Now what we're going to do, so I'm going to phrase everything in terms of French to English. So there's two caveats that we need to consider. First, when I write something in English versus write something in French, French and English are not necessarily the same length, right? Like you could need more words in English to represent the same thing that you would need in French, right? So it's really just a token thing, right? Like how many words do I need to represent? In English could be longer or shorter. It depends, right? Depends on the language. And so when we're doing English to French conversion, these are of different lengths. So now we have English can be of length L, French can be of length N. On the other hand, the embedding dimension is the same. We want to make sure these are the same, otherwise this wouldn't really be possible. So we're going to make sure the embedding dimension is the same, but the length of each of them are different because there could be more or less French or English or whatever. So we have that. What we typically do is the thing we want, right? Remember, the queries is the thing that we want, and the keys and values is what we want to weight against. So if we want to generate French, then we want to understand how is the French related to the English, or how is every token of the French related to every English of the French, and then we're going to weight it that way. So typically our queries will be the French, right? It's the thing we want. So queries will be the French. The keys and values will be the thing we want to weight against the English. And what this looks like is this. So what we have here is our queries is going to be N by E. This is our French. And our K transpose will be E by L. This is going to be our English, right? But transposed. And it produces an N by L attention matrix. So notice our attention matrix now is no longer a square. It's N by L, right? Depending on how long our English and how long our French are. And then we multiply this by our value. So this is a representation of how is the first, it's N by L. N is our French. So how is the first word of the French related to the first word of the English? How is the first word of the French related to the second word of the English? How is the first word of the French related to the third word of the English? ... So how is, and then the next word would be how is the second word of the French related to the first word of the English? How is the second word of French related to the second word of English? Second, so on and so forth. So we're learning how every word of French along this dimension is related to every word of English along this dimension. And now this is our English embeddings, right? This is V is just another projection of the English, right? Another projection of the English. So now I can weight, okay, French is related to English by the first French word is related to the first English word by this much, second English word by this much, third English word by this much. And so why not just average it up? I can do an N by L times an L by E, which will tell me, well, I have let's say the first French word is 5% related to the first English word. So I want 5% of the first vector, 10% of the second vector, 50% of the third vector, ... So we're weighting our values vectors, each of these vectors representing an English token, we're weighting them by the relationship of what our model thinks how the French is related to the English. So in the end, our input to this model is French and English embeddings. The output is basically weighting the English embeddings by how much the French embeddings were related to them. A little weird to think about, but that's the main idea. And cross attention will look something like this, right? How are the different French tokens related to the different English tokens, right? So we'll learn some matrix like this, and we weight by values, right? So we can see that, oh, we have the first French token's 0.1 related to the first English token, so I'm going to grab 0.1 of V1. I'm going to grab 0.1 of V2, 0.2 of V3, dot, dot, dot. And then the second one says, oh, the second French token is related 0.2 to the first English word. So we're going to grab 0.2 of V1, 0.4 of V2, dot, dot, dot. And again, these are all softmax to add to 1. So nothing has changed. Do realize that. Nothing has actually changed. It's just that instead of QKV coming from the same X, we now have Q coming from one thing and KV coming from the other thing. And the key idea is that, it's a pun, but yeah, the key idea is that the queries is the thing we want to output, right? If in the case of generating French from English, French is the thing we want, right? We want to generate the French. So we need to do the cross attention with queries being our French and the keys and values being our English. In the case of some of the transformer implementations out there, like I think in like PyTorch, this is known as the target, right? So the French is our target, the thing we want. The English would be known as the source, right? So we have a target, we have a source. So nothing changes. Right, the other thing, padding, right? So you can imagine that we need to batch our tensors together, right? So we're gonna have some English, right? English, and we're gonna have some English tokens, right? Word 1, word 2, pad. Word 1, word 2, word 3, word 1, word 2, pad, right? So our English, when we take our English sentences and concatenate them together, we're going to have some padding tokens, right? Because every English sentence is of a different length. But then we also have French, right? Our French, which will also have these, and these will be word 1, word 2, pad, pad, right? And then the third, it could be pad, and then like another pad. I don't know. Like, you get the idea. So we could have another pad here. So word 1, word 2, word 3, word 4, word 1, word 2, word 3. So when we concatenated our French together, again, pad tokens appear because not every sentence in French is the same. The important part is they're one-to-one correspondent, right? So this English sentence goes with this French sentence. This English sentence goes with this French sentence. This English sentence goes with this French sentence. But when we stack them together, we end up with these additional pad tokens. How do we deal with them? Well, exactly like what we did before. We want to learn how the French is related to the English. What we don't want to learn is how the French is related to English pad tokens. It doesn't mean anything, right? The pad tokens are just filler. So we will zero out, just like before, the columns of our attention matrix that correspond to the English pad tokens. So we're going to have two things now. We're going to have a source attention mask, and we're going to have a target attention mask. So because we have two tensors, right? We have English tensors and French tensors, right? In batches. We're also going to have an attention mask for the English, indicating which words are pad and which ones are not. And we're going to have another attention mask for the French. And because the French is our target, that's typically known as the target attention mask. And because the English is our source, that's typically known as the source attention mask. So there we go. So let's go ahead and implement cross attention. When I say implement, there's really nothing to implement. There is one thing to keep in mind. There is no such thing as causal attention in cross attention. That doesn't make any sense. Like, there is no causality here. We just want all of the English we have to look at all of the French we have, and that's it, right? The causality is induced by the causal self-attention, right? But everything else is just like this. So there we go. Let's go ahead and take a look here. So our cross attention, everything is the same. So I'm going to copy paste our existing. So let's just take self attention because we don't need the causal stuff at all. I'm going to grab you, put you right here. As you can see, we're kind of implementing the same thing over and over again, right? We're not doing anything crazy here, but our data will look kind of like this. We have English and French. Pick some embedding them, some num heads, and we're just we're just doing exactly what we did before. We're just generating we have French data and English data, and we have French masks and English masks, which produces something like this. And let's probably throw an error. That's fine. We're gonna, let's call this cross attention, right? So cross attention. Yeah, we haven't written the forward function yet, so that's fine. But I just want to take a look, right? We can look at our, here's our English masks, here's our French masks, and then we have the corresponding, embeddings that go with them. So this should all be familiar. We just did everything twice rather than once, right? Nothing new has happened. But our forward function is now going to get two things, a source, a target, and an attention mask. So now we're going to have, I'm going to call this source, a target, and an attention mask. Okay. It's still throwing errors. That's fine. We're not there yet. So we pass in a source and target. The source in this case is the thing we want to compute our weights against, like English in this case. And the target is the thing that we want, so French in this case. So like I mentioned, we're going to compute the queries on the thing we want, but we're going to compute the keys and values on the thing we want to weight against. So there we go. We also need, so we don't have just a sequence length now. We have a source sequence length, right? We have a source sequence length. And then similarly, we're going to have a target sequence length, right? So we have our source sequence length, because they can be of different sizes, as indicated here, right? So we have different lengths. So we have these, because when we do this reshaping and stuff like that, we need the sequence length, right? But this query will be based on the target sequence length, and the keys and values will be based on the source sequence length. But everything else stays the same. So nothing else changes. Now that we have that, I believe that QKV, attention. Okay, let's see. Right, so we have one more thing to fix. So print attention mask. Okay. Here is our attention mask. Okay, so key idea. Our attention mask, we want to mask out the columns of English, right? Or in our case, the source. We want to mask out the columns of the source that are indicated as something we don't want to compute attention on, which means our attention mask is just the English mask, right? The English mask. We actually don't need the French mask in this case. We need the French mask. We'll talk about that when I give the high-level picture in just a bit, but for now we don't need the French mask. We just need the English mask. So we're going to go ahead and just pass in the English mask as our attention mask, because that tells us which columns of this are English pad tokens, right? So pad tokens. So if we look at our attention mask dot shape, it will be exactly what you think. It's a 3x5, which makes sense because our longest English sentence was 5 long. So everything's been padded to 3x5. But our print attention dot shape, right, is a 3x3x7x5. So this 3 is our batch size. This 3 is our num heads. This is the length of the longest French thing, right? So French tokens, and then by 5. So we need to first add our unsqueezes, just like we did. So we're going to do attention mask is equal to attention mask dot unsqueeze 1 dot unsqueeze 1, right? So we've added those dimensions. And again, PyTorch will automatically broadcast this for you, but just to be consistent with what Flash Attention wants later, we're going to go ahead and repeat this one 7 times. So notice that we need to repeat this pad token, the fact that these two need to be 0, however many French tokens we have, right? We repeat it French number of times, or whatever the length of the French is. So this will be the target sequence length, right? So we're going to repeat this. Instead of sequence length number of times, we're going to repeat it 1 by 1 by target sequence len by 1. So now we have a 3 by 1 by 7 by 5 and a 3 by 3 by 7 by 5, right? So we're good to go there. We have everything we need, and we can now go ahead. We don't need U anymore. We can print out the attention mask real quick, just so we can see our final effort. Again, there's no causality here. All we're doing is, in every sample, masking out the columns. We see the last two English things are false, so these are all false. And then all of the things in the second one are true, so that's true. And then the last thing is false, so that's false. So that's our attention mask. Nothing crazy. Exactly like what we had already looked at. And so our attention mask is everything else is the same. We do a masked fill. Now we still have an issue. This is about this bug here, so we'll get there. Let's comment all y'all out, and then print x dot shape. Right? Where are we at right now? X dot. Oh, let's not return x. So it's not printing everything out. There we go. So x is currently a 3 by 3 by 7 by 6, which makes sense, right? We have sample of 3 heads, and each thing is a 7 by 6 tensor. Okay. Actually, 7 by 6 seems a little incorrect. What are we missing here? Let's just check our operations as we go, just to double check. Print attention.shape, right? So what we've gone ahead and done here is our attention computation. 3 by 3 by 7, 5 by 5 makes more sense. Okay, that's good. Oh wait, no, of course it's 6. Yeah, never mind. Yeah, we're good. We're good. The reason it's 6 is because our embedding dim is head dim is 6, right? Because it was an embedding dim of 18 divided by 3. That makes it 6. So yes, so this should be a print x.shape is 3 by 3 by 7 by 6. And now just like before, we're going to permute, right? So we're going to flip the 7 and 3. So it becomes 3 by 7 by 3 by 6. So that's going to be x.transpose. Comment, get rid of that for now. And we can print x.shape. Okay. And now that we have our x.shape done, right, we have these. And now we can put this 3 and 6 back together to produce 18. So it'll be batch sized by, this is the French target length. So it's throwing an error because originally it was just sequence length, but really it needs to be this target sequence length by embed dim. And that gives us 3 by 7 by 18, which is coincidentally what our, if we print tgt.shape, that's exactly what we started with, 3 by 7 by 18. I hope that makes sense. So again, oh, and then of course, all of this stuff stays the same. So there we go. So the main idea, again, is, let's do here, get rid of you. Oh, there. The main idea, again, is really just this figure. We will compute the queries on the thing we want, the keys and values on the things we want to weight against. The input is our French and English. The output is a weighted average of how the French was related to the different tokens of English. And so that's our context vector. And so going back to this idea that I mentioned, we have a couple things happening then. In multi-head attention, so this is our inputs. This is the English. So English goes down this track here. And it learns how different English words are related to the other English words in our data, right? In that sentence. So this is our encoder for English. After that, so this can be bidirectional. The reason it can be bidirectional is because we're not generating anything. We can look at when I want to translate something, right? I have the whole sentence. I'm asking the LLM or this model, like, here's my English, the whole English sentence. I want you to translate it to French. So because I have the whole sentence up front, you can look at it bidirectionally. Future words can look in the past words can look in the future, whatever it wants. On the other hand, the French has to be generated. And we're going to talk about how we actually use causal masking as a mechanism to generate tokens in the next video. So we actually, write the generative function. But the causalness, the causality ensures that when we generate things, well, when you're generating something, you can't look into the future. There is no future, right? You're generating. There's no future to look into. So when we're generating, we can only look into the past. So that ensures that we have a French that's being causally masked, right? We're causally masking the French here because we can't look into future French because there is no future French. We can only look into the past French to generate future ones. This is where the French mask will be used. So we have the French padding mask because this will just go back to exactly what we had before, where you have both a causal mask and a French padding mask, right? We'll have both of them. So that's where this would come through. And then this is to tell me, okay, I've generated a French. How is, I've learned how my current French is related to the previous French, right? Because this is causal. How is all the French I can look at, right? So you're restricted by what you can look at. How is all the French I can look at related to the English? And this is the cross attention portion, right? And then using this information of, oh, this is how I'm related to the English. I guess this is the next French word I should generate. This is kind of the general principle of this, and we'll program this in detail in the next couple videos. But for now, this is just to give you an idea of what causal attention is. So this causal attention, again, as you notice, nothing changed. We just have this extra little bit here. And so now let's just go back to the last part, flash attention. So this was something put out by Dow Labs. So let me pull up their Git repo actually, so I can show you what they did. This might be a little bit tough for me to explain all the details, but I can give the general idea. So there's there's actually a couple, but there's a couple limitations that attention has. The first one is the quadratic complexity. So I know I haven't mentioned this too much yet, but we can actually prove this immediately by just looking at any one of these pictures. So let's look right. Let's see here. Attention. Okay, let's say this for now, right? So the attention mask produced by a sequence of length 4 is 16, right? We have 16 elements in this matrix, a 4x4 matrix. What if your sentence had 1,000 words? 1,000 words is not a very long sentence. That's roughly an essay, right? But if you have 1,000 words in your text, then this matrix becomes a 1,000 by 1,000 square with 1,000,000 elements in it. So there's a huge quadratic complexity when it comes to this. And so the amount of GPU memory and compute necessary to actually pull off long contact sequences becomes tougher and tougher as you work on it. By the way, that's just general idea, right? That's a limitation, the quadratic complexity, and there's lots of open research right now on how can we do this better. But flash attention proposes one way of at least doing it more efficiently. The entire thing that we've been doing here, we first do a QK transpose, then we apply a softmax, then we apply a dropout, and then we multiply all of this stuff that we're doing here, the formula, right, for attention. Each of these are basically a new operation running on the GPU, and it adds to the compute cost. You can think about it, right? It adds more compute cost to what we're trying to do. Is there a way we can do it faster? Well, yes, there is. So this is what the attention mechanism, or what flash attention proposes. They basically write IO aware. IO aware means basically it's aware of the hardware that it's running on to optimally run the operation. So instead of notice that there's a matrix multiplication. We first do a matrix multiplication, then we do a masking, then we do a softmax, then we do a dropout, then we do another. This is your operation, right? QK transpose, mask it out, do the softmax, do the dropout, do the MatMul, right? With the values, do all of these operations. You could do all these operations. This is how PyTorch would do it. Or you could have a fused kernel. So they have a smart kernel. So when you're actually loading, that's what this kind of shows, but when you're basically loading your data onto the GPU memory, before offloading them, you can actually do a bunch of these operations at the same time. You don't need to load memory and then offload them and then load them again and then offload them for every single operation that we do. You can actually load it once and fuse a lot of these operations together. And so that's what flash attention does. It takes all these operations and does them all at the same time on little chunks of them is the most I could say. If you're an expert in CUDA, then you probably don't really need to watch this video because you probably know all this stuff anyway. But yeah, if you understood CUDA and how the CUDA grid system works and how basically operations like this are parallelized, then it makes a lot more sense. TLDR, flash attention is great. It's super fast. makes your life easier. And we typically, if you're going to train a big bad model on lots and lots of data, then why not take advantage of, something that is as fast as possible? So what I'm going to do now is write one more attention mechanism, and this attention mechanism is going to be exactly what is implemented in our future video. So I'm going to assume this code is written when we go on to work on the actual attention is all you need implementation. So this attention mechanism will already have been done, but let's go ahead and write it. What I want to do is write one unified attention mechanism that handles all of the different situations that we've talked about. So it needs to be able to do basically everything I've mentioned. Like if we pass in just one thing, then it does self-attention. If we pass in one thing with its attention mask, then it'll produce, it'll do self-attention with its padding mask. If we pass in one thing with its attention mask and its causal, then it'll apply the attention mask and the causal mask to that thing, to that tensor. If we pass in two things, right, like the English and the French, then it should do cross attention, right? That's basically it. So we're going to go ahead and do this. Class attention. Again, we're just going to copy paste this whole module into our next video, right? When we actually go on. But for now, we're just going to go ahead and do this. Embed dim. Let's put these some reasonable defaults, 768, num heads, so it's gonna be 12 heads of computation, and then attention drop is 0.0, and we have a proj drop is also 0.0. 0.0. Right, so there is all of the stuff we need. Oh, I forgot a equal sign. Whoops. All the stuff we need. And we have a def forward, and we're going to pass into the forward a self, source, target is none by default, attention mask is none by default, and causal is false by default, right? So if I only pass in a source and nothing else, I'm just going to do self-attention. If I pass in a source with an attention mask, I'm going to do self-attention with my padding mask. If I pass in source with attention mask and causal is true, then I'll have the attention mask, but I'll have the causality in there as well. And if I pass in source and target, target will be my output. Target is the thing I want, and source is what we're going to weight it against. So I guess that's what makes it a little bit unclear, but just to try to make this as clear as possible, if we provide the source is what we are going to weight the source against, right? We're basically weighting something against itself. If we pass in target, target is what we want, and it's going to be weighted against that source, right? So just to keep that in mind. But let's go ahead and do this. So we're going to first, actually, let's define the layers first. And the layers should look exactly like everything we have seen so far. Dot init. Right, so we're going to do self.embedding dimension, or embeddim is embeddim self.num heads self.attention drop is attention drop, and self.proj drop is proj drop, right? So there we go. And we're going to do self.headdim is, again, self.embeddim divided by integer division by self.num heads. Right, and just to be the most correct, we can do assert embeddim mod with num heads is 0, right? Make sure embeddim divisible by num heads, whatever, right? So it's just a quick assertion check just to, verify. And so everything else is the same. Self.qproj is going to be nn.Linear, and it's going to take embeddim in and embeddim out. And I'm just assuming bias is true. You could also add that flag in, but that's fine. And we need, 3 of these. And we're also going to need one more for the final proj. So we're going to call this qproj, kproj, vproj, and outproj. But other than that, they're all the same. So now it's time to handle our condition. So there's two possibilities. if target is none, oh, I somehow merged that. Let's. Okay, good. Okay, yeah, sorry about that. I don't know why that happened. Whatever. That's fine. Yeah, whatever. Okay, if target is none, right, then we can go ahead and do, this is then self-attention, right? Self-attention. Else, right, if target is not none, then we're in cross-attention, right? So these are my two options. And so if I'm self-attention, it's pretty straightforward. We just do exactly what we've done before. So we can just copy paste it. I'll just copy you and fix it. We'll have our QKV, right? QKV. These are now called, oh, I guess I changed the names again. That's my bad. That's fine. QProj, KProj, VProj. This will all happen on the source, right? Because there is no target, right? It's just the source right now. So QKV, transpose, everything else is the same. And then if attention mask is not none, right? If the attention mask is not none, then we go ahead and do attention mask is equal to attention mask dot bool. This is verifies that we're passing in a Boolean mask. If we didn't, then it will convert it to a bool. I'm again assuming, we'll actually look at the documentation in just a bit. But just like before, we need to do attention mask is equal to attention mask dot unsqueeze 1 dot unsqueeze 1 dot repeat 1 and it'll be source len. So we should actually go ahead and get that. So this is going to be the batch by source len by embed dim is equal to source dot shape. Right? So there we go. And we can also do if target is not. All right, we can throw that in the, we have that conditional anyway down here. We'll toss that in there later. So by 1. So this is exactly what we did before, right? Nothing new. We just added this extra dimension in because the flash attention expects that. And so how do we use flash attention? There is two ways. We can either use PyTorch or we can do a pip install on the flash attention package. So flash attention will have the more bleeding edge, like flash attention 3, I think is what they're at right now. So they will have the faster versions, but I want to keep this to Torch just so there's no extra installs for anyone. And for the scale at which we'll be building models, it's probably not as crucial. So I've been using flash attention, the PyTorch flash attention for everything and haven't had any issues. So you can do attention out is equal to f dot, and PyTorch calls it scaled dot product attention. Right? So this is what PyTorch, this is how they indicate flash attention, and it's under the functional f dot. So f dot scale dot product attention. And this needs the q, k, v is what it expects. And then it needs the attention mask is equal to attention mask. This will just be none, right? If there was no attention mask passed in. Dropout p is equal to self dot attention dropout. But remember, we only want to do dropout when we are training. We don't want to use dropout when we are evaluating, right? So we can do if self.train. So we haven't talked about this, but when we do model.train for training mode and model.eval for evaluation mode, it's actually this toggle that's flipping. Like self.train becomes true and false based on which one of these you set. And then the submodules like batch normalization, dropout, and stuff, take a look at self.train to decide, like, am I in training mode? So like, should I be doing something? Or am I in evaluation mode? So should I not be doing anything? So we want dropout if it's trained, else it's just 0.0, right? If we're not in training mode, then we have no need to do it. And then is causal equals causal, right? This will automatically build the causal mask for you it will layer in the attention mask for you, and it will do this entire attention computation for you. So all this stuff that you see right here, basically these couple lines of code, this does it. It just does it significantly faster than we could implement in raw PyTorch. This needs to be done at the kernel level. So that's why this is preferable. So we have our attention out. This computes our attention. So we're done there. So this is good to go. Else, right, if we're doing cross attention, things should look very similar, but we have to add in a couple of extra little things. So first of all, if we're in cross attention, then target is not none. So we can do target len is target.shape1. Right, because this will also be a batch by sequence length by embedding dim. So the the middle dimension is my target length. The Q is going for my target, so this will be TGT, and I need to reshape this to the target len. Similarly, this is, and actually let's update all of you. So source len. So when there's no target, everything's just source len. And when there is a target, we'll have target len, source len, source len. There we go. So this is our attention computation, right? Or the QKV computation, just like before. It's just, we have a query key value now. And again, if attention mask is not none, all of this stuff is the same, right? All of this is the same. But we won't repeat for source len, right? Again, if we remind ourselves, right? We'll repeat the attention mask however many French tokens we have. In our case, French is the target, or the number of rows is our target. So we'll repeat it target len number of times. So this is going to be target len, but everything else is the same. And then, just like before, our attention computation is identical. So we have F, again, QKV. In this case, Q is coming from our target, but it doesn't care, QKV. We have our attention mask, dropout, and causal will always be false here. There's no situation, I think, in where cross attention would have a causal mask. It just doesn't make sense. So there we go. And now that we're here, everything else in our code is identical. So we can go back, look here. We do a, so all of this has been covered. And we can just go ahead and copy paste the rest of you in. Right? Just put everything back the way we found it. Let's see. So it'll be batch by, and actually because our lengths change, I do it slightly differently. Because we don't know if we're dealing with the source or the target, so just so we have one line of code, we can rewrite this as dot transpose 1, 2, and dot flatten 1, right? So we'll just flatten it out so we don't have to specify like specific dimensions. So there we go. So this will take our batch by num heads by heads h by sequence length by head dim, right? And it'll convert it to basically batch by sequence by head by e, and then it'll just flatten everything afterwards, and we're basically good to go. And actually, no, flatten should happen on 2. So yeah, let's be clear. This will become batch by sequence by head by e, and then we want to flatten everything after the second dimension. So head and e should be combined, so that's 0, 1, and then 2. So flatten 2 says I want to flatten from 2 to the end. And that's it. So that clears it up. It'll be the same for the cross attention as well. So return x. So there we go. Now I'm going to copy paste a bunch of these tests in, but we're going to test every possibility that we care about. Let's do this first one. So we're going to test first self-attention. See if this works. Okay, looks like we have a bug. None is not defined because this none should be that none. My bad. Okay. QKV, looks like the shapes are off. So let's check here. 9, 3. So if target is none, then we have, okay, let's just verify some stuff. Good, so we can do print source.shape. Make sure this is what we expect it to be. This is going to be a 3 by 5 by 9, which makes sense. We have a batch size of 3. we have the longest thing is 5 and an embedding dim of 9. Okay, so that's correct. And then we are going to have head dim. Okay, so let's do print self.q proj source.shape. Let's check this. So this will be 3 by 5 by 9, just like before. So which line is it breaking on? 4 by, let's see. Yes. This should be batch size. There we go. He was using some earlier reference of batch size, I think. Okay, looks like we have another one. Attention dropout, so I must have just spelled it wrong. I think I called it just attention drop. So that's going to be here and here. And what else? Got is causal, spelt it wrong. So is causal and is causal. All right. Local variable x not defined, which makes sense because these both things will output something called attention out. So there we go. And then has no attribute proj because I called it out proj, like that. And do I even have a proj drop? I do, but this one I need to actually do self.proj drop is nn.dropout proj drop, right? So we don't actually need you. There we go. So we have our proj drop now. That'll apply it there, and there we go. So that's our self-attention, right? So we're good to go there. Sorry for the bugs. It's always the little things, spelling, that sort of stuff. So okay, so we have our self-attention. So this is self-attention with the causal mask. We can also have self-attention without a causal mask, right? There we go. Right, it's up to us how we do it. Again, we don't need to build the causal mask because flash attention's doing it for us. Right? So makes our life a little bit simpler. Let's now go ahead and test cross attention. So this one should just work, but I'm always surprised. Yeah, this one just worked. So again, this is cross attention. This is the example we had from earlier. We have some text, or like, fake lengths of text, generated some fake text, and then passed it in, and there we go. We now have cross attention. So let's do a big recap. I know this was a long video, so if you made it this far, congratulations. You probably understand everything you'll ever need to know, at least about the attention mechanism. But let's talk about why this is crucial and where this is going to show up. So let's go back here again. So the original attention is all you need paper was proposed as a language translation. So these are known as sequence to sequence models. So you have a sequence input and you generate a sequence on the output. And in sequence to sequence, we kind of need all of this stuff, right? So we have a something that encodes the input, and then something that decodes and generates a sequence. So this side is the encoder, and this side is known as the decoder. But we can actually take this model and break it up into pieces. For example, if we only look at this left side here, so ignore the right, this is your vision transformer, this is your BERT, this is your Roberta, this is your masked autoencoder. These are all your encoder type models out there. On the other hand, if we take this right side and ignore the cross attention, there's no cross attention. If we take this right side here and only have the masked multi-head attention and then the feed forward, this is your GPTs. This is your llamas. This is your Phis. This is all your big language models, anything that generates. And so basically there's 3 classes of models. There's sequence to sequence. You have a sequence input, sequence output. You have encoder models that take a sequence and they're bidirectional. They can look both ways, and they're typically good for summarizing information or searching for information. So examples are like image classification, right? You take a whole image, you can look at the whole image and you can classify something about it. Or text classification. You can take an entire, you can take text, you can look at the whole text back and forth and you summarize them and you classify something about them. Or for extractive Q&A, that's an example we'll implement in the future for Roberta, where I give you a sentence and I'm asking you a question, I'm giving you some text, like Priyam's favorite food is hamburgers and he went to the park today. And then the question could be, where did Priyam go today? And the question has to look at the whole thing, look at the text and say, oh, to the park, right? So these are just some examples of how the encoder, this left side, is used, and we're going to implement this multiple times in different ways. And you'll see that 90% of the implementation really doesn't change between transformers, which is nice. It's how we prep the data that gets really tough. And we're going to have some easy times with it when we do vision transformer, masked autoencoder, stuff like that. It's going to be slightly harder when we do Roberta. It's going to be very hard when we do the wave to vec implementation as well, right? So that's a challenging one. On the other hand, the decoder is what generates text. It's something it's a generative model. So this is, again, like all of the ChatGPTs of the world. Anything that can generate text is a decoder, right? So that's just how it works. And we'll be writing a couple of these as well. So we'll see how far we can get. But that's it, right? Again, recap. The attention mechanism is our way of avoiding recurrence, but still learning the sequence task. The problem with attention always comes down to permutation and variance, which we'll talk about next time, but basically it has no idea of order. So we need to inject some type of, like information about position, like where is something with respect to other things. So we need to inject that information in there. And we have some methods to do that. But it lets us avoid a painful RNN. The penalty that they saw, though, is it requires significant amounts of data to train, right? Significant amounts of data to train. So there's a great paper, Neural Scaling Laws. Let me find it. This is a paper from OpenAI, I believe, from a bit ago, where they talk about scaling laws. So how, what is the complexity of the model that you can expect, and how much data do you need to train, and that sort of stuff. And the data cost has skyrocketed for a lot of these transformer-based architectures. They require lots and lots of data. A part of it is because that implicit bias that, hey, like this time step comes after this time step, which comes after this time step, that was baked in to the RNN. That was already there. But now the model has to learn this extra stuff as well. Like it needs to learn positional information. It's not just about text anymore, but how words are positionally related to each other is another part that the model has to learn. So the complexity has gone higher, and the more stuff the model has to learn, the more data you need to train it. But yeah, either way, so we implemented a self-attention mechanism. This figure should now make sense, right? We have a input, 3 linear layers to produce queries, keys, and values. Queries and keys come together to produce an attention. We weight our values by the weights in the attention, project it, and produce an output. So we trained attention. We looked at a encoder, what an encoder is, what is causal masking, what does it mean to be a decoder, again with the causal masking, a simple example of a single head of attention, an efficient implementation of a multi-head attention, how do we incorporate padding masks into our model, then how do we incorporate the causal mask into our model, and then again, how do we incorporate both causal and padding masks into our model, which is something we'll need. And then how do we do cross attention, which is something we're going to need. And we've covered every variant. So this was a super long video. I'm not really sure how long it's been, but it covers basically every format in which you will see attention being used. And we're going to be basically using this stuff in slightly different ways for all of our future implementations. So the next video, we're going to do this. So we looked at multi-head, we looked at masked, we looked at, basically orange blocks are done. We still need to write the feed forwards, which are super easy. They're just 2 linear layers. We need to write the input embeddings and the output embeddings. Again, these should be pretty easy, but we'll be using something known as a sine cosine embedding to do these. And, that's the positional encoding. We need to write the positional encoding. The input and output embeddings are just embedding matrices, right? Just like the ones we saw in the LSTM to convert tokens to vectors. And we just need to construct the transformer block. So this will be our first step into implementing the attention is all you need. The next video, I think we'll write the model, and then the video after that, we will write the training script, or maybe I'll do it all in one video. I'm not sure yet. So we'll see based on time how things go. Either way, we're going to call it. This was a long video. If you have any questions, comments, concerns, drop it down below. Let me know if there's any feedback. I hope this is helpful. The stuff regarding the padding mask really confused me when I was first doing this, so hopefully this clarifies some stuff for you. Either way, I will see y'all in the next one.